So what we are going to do today, we are going to cover another very important aspect of inferential statistics. And I have said already in the first lecture that is now available online. The goal is we are going to today we are going to cover a very specific aspect which is called hypothesis testing. And the goal is determining when a particular hypothesis that we formulate about a certain population is correct, is right, or it is not. And obviously, um, a possible solution when you're facing the type of problems is you can go to the entire population and you can study every single element in your population. That will solve the problem. However, that is very costly in real life. Sometimes it is really impossible to study every individual element in the population. Sometimes it's also impossible. Suppose that you are producing some kind of electronic component for computers, and suppose that you want to assess what is the lifetime of these components. And the way you have to assess that is you will make this component to work until it fails. Obviously, you don't want to study their entire production population because you would end up breaking all your components or your electronic components. So you are forced in such a situation, for instance, to work with a sample. And this is a case in which the experiment, for instance, ends up destroying the experimental unit you are using. But even in the less dramatic case, is sometimes just not feasible to study an entire population. We saw an example in the previous lecture. If you want to answer the questions, are women and men earning the same by if they are having the same job? This is a very important sociological question. Is if you want to answer that question, a possibility is just to do a kind of census in which you ask the income for every working women and men in Belgium, for instance. But we are talking here about millions of people. And Belgium is not such a big country, and still it will be quite prohibited to carry out such a study. But it's also necessary. You can just answer that question in a reasonable way, not using or not studying the entire population, but for instance, studying 500 men and 500 women. The question, of course, here is, can I say something about millions if I only have information about 1,000? And the answer is yes, it's possible, but you need to follow certain scientific principles. And these are the principles that we study in inferential statistics. So it's fine. You don't need to study all elements of your population. You can work with a sample. But then, of course, you need to take into account sample variability. If you repeat your experiment exactly under the same conditions, but you use another sample, then your results are going to vary. This is called the sampling variability. And why samples vary? For instance, if you're dealing with patients, because there are biological variability in the population. Individuals are not identical, etc. So we need to take all these aspects into account. And let's start by an example. Is the birth weight example. Here you have a research journal publishes a paper some time ago, and they stated in this research, they estimated that the average birth weight in Flanders is about 3,3 kilograms. Now, you have a gynecologist that is having his practice in Limburg, and he speculates that the average birth weight in Limburg may be different than in the average in Flanders. Why? Well, it's a quite, let's call it, it's an area in Flanders that has a lot of nature. Life is a little bit, let's say, less complicated. Move at a lower speed. We are not talking about Brussels, Antwerp, big urban areas. And he speculated that all these conditions may have an influence on the birth weights of babies. So that's a scientific question. That's a scientific hypothesis. Now, how we can assess if this hypothesis is correct? He has his theory, he has his scientific elements, but ultimately in science, we need to test hypotheses on data. So how can we do that in this specific example? Well, we do what scientists do. We gather information. So he gathered information about 30 babies. And what we have here on the right side in that table is the information, the data he gathered. We have 30 experimental units. In this case, we are talking about babies. And for every baby, we have the birth weight. Now, how can I use this information? We have now information about 30 babies. How can I use this information to try to evaluate a hypothesis about the population of all babies in Limburg? That's the question we are trying to answer here. So let's start developing some notation. We are going to call mu L, L because of Limburg, we are going to call mu L the average birth weight in Limburg. This is a quantity that is fixed, but is unknown. Is unknown. If we want to know that, we will need to weight all the new babies in Limburg, and it's a dynamic population because every day new babies are born. So it's almost literally impossible to estimate that value. But or to know it precisely. But we can have an idea about this if we consider the sample, the data he gathered. Now he has a hypothesis regarding his population. He has a question, and the scientific question is the average birth weight in Limburg the same as in Flanders? That's the scientific question we want to answer here. Now, based on that question, you can formulate two hypotheses. We can call a null hypothesis, that we call it null because it's always the hypothesis that refers to null effects, nothing going on, nothing is happening here. And in this case, the null hypothesis will be there is nothing special going on in Limburg. The average birth weight in Limburg is the same as the general average in Flanders. So the null hypothesis is null effect, null association, nothing going on. In this case, it could be it is the same. There is no special situation here. The average birth weight in Limburg is 3.3, like the average birth weight in Flanders. And then we formulate an alternative hypothesis, which is it is not the same. There is something going on. There is an effect. There is an association. That's the way we formulate the alternative hypothesis. So we start here with a question, a scientific question, written in terms of words, normal English language, and we now reformulate this scientific question into two hypotheses. One that accounts for a negative answer, there is nothing going on, null hypothesis, and one that accounts for a positive answer. There is something going on, they are not the same. Now, we can reformulate this null hypothesis now in the following way. The null hypothesis means there is nothing going on, so mu L, the average birth weight in Limburg, is 3,3, like it is in the general population in Flanders. That is my null hypothesis. And the alternative hypothesis would be, no, it is not 3,3. There is something different going on there. And now our scientific question that was written in number language, like we did at the beginning over here, has become a mathematical issue. We have rewritten our scientific question into two mathematical hypotheses. So now I need to use my data to decide which of these two hypotheses I will find more plausible. Are we going to accept the null hypothesis and say, well, actually, there is nothing going on in Limburg? Or are we going to reject it? And then that will mean that indeed there is some special situation going on there. Well, that's what hypothesis testing is all about. It's about using the data to try to assess the likelihood or the plausibility of a scientific hypothesis. Now, how we can do that? Well, there are three main methods to do this. We can use something called a critical region. Is the first method we are going to see here. We can use a p-value, or we can use confidence intervals. We saw in the previous lecture. There are three main procedures to test hypotheses: critical regions, p-value, confidence interval. These two approaches here, the critical region and the p-value, are two different philosophical approaches. Even though in practice, you will see that people frequently mix them up. When we analyze problems in practice and we calculate p-values, for instance, we talk about p-values and we talk about type 1 errors at the same time. However, type 1 errors and p-values are two different philosophical approaches to the problem of hypothesis testing. But in practice, people mix them up, and we are going to see later on why. And the third approach, which is based on confidence interval, is less used in practice, even though it may be the best way to go. And we are going to illustrate that also later on. So here you have these two gentlemen that you're seeing here are Niemann and Pearson. And they are, well, together with Ronald Fisher and many other big names in our field, two of the most important statisticians of the last century. And they created around the 1930s the formalism of hypothesis testing. They created the methodology based on so-called critical regions. Before then, at the beginning of the 1920s, Fisher had proposed a different method to test hypotheses based on p-values. And that was for sometimes the dominant methodology. But in the 1930s, Neiman and Pearson came with a different formalism based on critical regions, type 1 errors, type 2 errors, power of test. All these concepts are belong to the paradigm of Neiman Pearson, not to the paradigm, the Fisherian paradigms of p-values. And as you will see, people ended up like kind of creating a hybrid, a mix between the two procedures. Now, we are going to differentiate two types of tests. We are going to talk about parametric tests and we are going to talk about non-parametric tests. Now, what is the difference between these two scenarios? Well, a parametric test makes an assumption. It assumes that the data come from some probabilistic distribution. So when you use a parametric test, you assume that your sample, the individual observations in your study, have been generated by a common underlying data generating mechanism, and this data generating mechanism is a probabilistic model. So for instance, you assume that your data are normally distributed, or you assume that your data follow an F distribution. So you assume that the mechanism that generate the data can be modeled with a probabilistic model. For instance, we saw in the previous lecture that IQ scores follow the patterns of a normal distribution. Now, when you administer an intelligence test to a person and you quantify that score, what generates that data? From where that number comes? Well, an IQ test is some kind of like an exam. And I can imagine that there is a very complex process that takes place in the brain of this individual, and is this reasoning that he uses to answer these questions, and this is at the end of the day quantified in an IQ score. Well, this is a very complicated process, and we assume that that complicated process can be modeled with a normal distribution, that there is an underlying data generating mechanism that is a probabilistic mechanism, that is a probabilistic model. And then this probabilistic model depends on certain parameters, and we formulate our hypothesis in terms, our scientific hypothesis in terms of these parameters. Like in the case of Bird's wave we have just seen, in the previous lecture we saw that Bird's wave follows a normal distribution. So we assume that the mechanism that generates these birth waves, imagine how complicated that is. That depends on so many factors. Genetic factor from the mother and the father, how the mother eats, how she moves, how it depends on many, many, many factors. But this complex process we are modeling with a normal distribution. That normal distribution depends on two parameters, and we formulate our scientific hypothesis in terms of the parameters. That's parametric statistics. Now, non-parametric tests or non-parametric statistics follows a different path. What we do is that that we assume that this generating mechanism, this data generating mechanism, doesn't have any specific form. We still assume that there is some kind of underlying stochastic process generating the data, but we do not specify it in a probabilistic model like a normal distribution, a Cauchy distribution. We leave it there at a high level of generality. So we cannot formulate the scientific hypothesis in terms of parameters because we do not specify the parametric probabilistic model. We just said the data follows a distribution, period. So these are two big domains. Of course, non-parametric statistics is more general because the more you specify your model, the more chances you have to get a mistake. If you leave it very general, of course, your chances of committing a mistake are smaller. But at the same time, you pay a price for that, and the price is in terms of power. Parametric tests, everything equal, tends to have more power. And what that means is that with a parametric test, there may be a difference that you can detect with a parametric test. For instance, if you're comparing two groups, there may be a small difference that can be detected with a parametric test, but will be invisible, undetectable with a non-parametric test. Assuming, of course, that the assumptions of your parametric model are more or less okay. We are going to work here basically with parametric tests, with parametric statistics. Okay, Let's say set the general framework. You need a null hypothesis and alternative hypothesis to do this type of research. So you need to formulate your scientific questions as a null hypothesis. As I said, typically no effect, no association, nothing going on, an alternative hypothesis. And then in the paradigm of Neyman-Pearson, that is the first one we are going to see, you need to define something called a rejection region. And that rejection region is based on a test statistics and a critical value. What is that? We are going to see it later on. And then you need to define what we call a type 1 and a type 2 error. These are the three basic elements we need. We need two hypotheses. Neyman and Pearson said you need to define a critical region, a rejection region, and then you need to specify two type of errors, type 1 errors and type 2 errors. We are going to see each of these elements in detail. Now, a little bit about a definition. What is a hypothesis? When we are talking about you need to define a hypothesis, what is that? A hypothesis is always a statement about the population. It's never a statement about the sample. There is nothing to hypothesize about the sample. You have the sample. You see it. You don't need to make hypotheses about it. So a hypothesis is always a statement about a population, about something big that you cannot, in principle, measure or assess. And the statement is usually made in terms of a null hypothesis, conventionally denoted by H0, and an alternative hypothesis, conventionally denoted as H1. And this hypothesis is typically formulated in terms of parameters, the parameters that govern this probabilistic model that you believe has generated the data. Now, hypothesis can be of two types. You can have what we call a simple hypothesis, and you can have what we call a composite hypothesis. Now, a simple hypothesis, what is that? A simple hypothesis specifies completely the distribution. Is, for instance, when you have you are assuming that your data are generated by certain probabilistic model like here, and this probabilistic model depends only on one parameter. A simple hypothesis will be a null hypothesis that specifies completely the value of theta. You say theta is equal to theta 0, and theta 0 is a constant. It's something not. It's 2.3, for instance. In that case, the null specifies completely the distribution, because when you specify the only parameter in your distribution, the distribution is completely specified. That's what we call a simple hypothesis. Well, it's a composite hypothesis. For instance, sometimes the alternative hypothesis is frequently composite. You say it sounds like, well, the null hypothesis is that theta is equal to theta 0, right here, the completely specified the distribution. The alternative is that theta is positive. It's larger than theta 0, for instance. Typically, theta 0 is 0. That will mean many times if you have a regression model and you have a coefficient in your regression, the null hypothesis is the coefficient is 0. Beta is equal to 0, no effect. And the alternative hypothesis may be, for instance, beta is different from 0. And as you can see, this doesn't specify completely the distribution, because different from 0 can be -1, -2, -3, 20, 25. And so you have these two types of hypotheses. Simple hypothesis is frequently what you have under the null, and then composite hypotheses are typically what you have under the alternative hypothesis. What is a critical region? So I told you we will need a hypothesis. We have defined now what that is, and they have two different types, simple and composite. We have seen that. I told you that you need also a critical region to evaluate your hypothesis. That's what we are going to do now. And later we will see what we mean by type 1 and type 2 error. What is a critical region? There is a very intuitive way of thinking about it. You remember we are developing all this in the Frequentis framework. And Frequentis have the following mindset. Frequentis said we are going to create methods to analyze data, right? Frequentis said we are going to create methodology to extract value from data, to extract conclusions from data. And Frequentis said, well, I want these methods to be good. But what do you mean by do good? When you're going to say that the method is a good method? And Frequentis proposed the following. Well, I'm going to imagine that I repeat my experiment several times, again and again, under the same conditions. I repeat my experiment again and again and again. Of course, the data these experiments are going to generate vary, right? It's sampling variability. You're not working with the same people. There is sampling variability. So you're going to get different data sets. And you're going to use this methodology you develop in each of these data sets. And then Frequentis will say that this methodology is good if it gives good results, correct results most of the time. So the idea behind critical region is a little bit of the same idea. Suppose that Y is the data set you observe. So these are your data. So if you're measuring birth weight, Y will be, for instance, in the case study we have just seen, is a vector with 30 components, the birth weight of the 30 babies in the study. So that's your data set. Now, you can imagine that you repeat this experiment again and again and again, and you get different data sets. You get different samples, right? The first 30 ways in the first experiment, the second 30 ways in the second experiment, the third 30 ways in the third experiment, and so on. That's a thought experiment. So suppose that you repeat your experiment and you will get different data sets. The critical region are those data sets that will be incompatible with the null hypothesis. Those data sets that if you get them, you will be getting evidence against the null, because that data and that hypothesis are not compatible. And we're going to define more precisely later what we mean by not compatible. But essentially, the critical region is a subregion of what we call the sample space. What is the sample space? The sample space is the space of all possible data sets that you can get out of your experiments. If you repeat them again and again and again, you can imagine all possible data sets, outcomes that you will get. And now you will define in that space of all possible outcomes of these repeated experiments, you're going to define a region. And you say, okay, if the data set that I actually observe falls into that region, then I don't believe the null anymore. Why not? Because you construct that region in such a way that the elements in that region are incompatible with the null. And that was the idea of Neiman and Pearson. They work about critical regions, no p-values. In the Neiman-Pearson paradigm, there is nothing like a p-value. It's a region. You look at the data and you see if the data belongs to that critical region. If it's there, then you reject the null, because in that region you have the experiments that are incompatible with the null. How do you construct such a region? Well, typically what you do is you calculate a statistic of your data. So it's just a formula. You take your data set and you do some operations with it. And if these statistics, these results give you a value that is larger than certain constant C, then this data set belongs to the region. So the region is defined as all the data sets Y, all the outcomes of your experiment, possible outcomes of your experiment Y, that satisfies this condition here. And the only thing you need now to completely specify your critical region, you need to determine the value of C. Once you determine the value of C and you get a data set, you just calculate this formula. And if it is larger than C, then your data belong to that region, the critical region, the rejection region. And that means your data is in that place that is incompatible with the null, so you will reject the null. So typically, this W is just, here you have the vector of observation. In our case, N is equal to 30. So this will be the 30 birth ways. You calculate an statistic based on your data. And if the result is greater than C, you say, well, my data and the null are not compatible. I'm going to reject the null hypothesis. What you need to do is you need to calculate this C now in a smart way, so that this region, this procedure we are creating now based on this region, this procedure has nice properties. And how you calculate this C? Well, typically what you do is you assume that the null hypothesis is true, and you see what could be the distribution of these statistics. Typically, or you calculate the distribution in a mathematical, exact, precise way, or you know that this asymptotically, this statistic has certain distribution D under the null. So you consider that the null hypothesis is true, and you try to find out what is the distribution of these statistics. And based on the distribution, we are going to calculate this value C. And once we have C, we have our critical region. And then the only thing we need to do is, you did experiment once, give me the data. I do my calculations and I tell you it is in the critical region, you need to reject the null. You repeat the experiment, you give me a new data set, I see if it is in the critical region, and I tell you, no, it's not in the critical region, you don't have evidence to reject the null. And that's what we are going to do. We are still going to see details, more details shortly. So we have two hypotheses, the null and the alternative. We define what a hypothesis is. We saw that they may be simple or composite hypotheses. Then the second element was to define the critical region. I told you it's a sub-region in the sampling space. And that is the space that contains all the possible outcomes of your experiment. And a critical region is a subregion there. If you do your experiment and your data set falls there, you reject. If you do your experiment and your data do not fall there, you do not reject. Now, how to construct this critical region? We saw that everything comes down to determine this value of C over here. And I told you we are going to use the distribution of the statistics under the null to calculate this C. But okay, how we are going to do that? Well, Neiman Pearson, they said the following. They say a test is a decision rule, period. That's a test. It's a decision rule. You are going to use your data to make a decision. And the purpose of hypothesis testing is to determine whether there is sufficient statistical evidence to reject a hypothesis. That's what it is. So it's a decision rule, and you're going to use your data to see if I have enough evidence to reject. The decision you're going to take is reject, do not reject, period. Nothing more, nothing less. We are not going to say borderline significant, no. For Neiman Pearson, you reject or you do not reject. It's a binary answer. And a test is just a rule to make that. Reject, do not reject. Now, the problem is that whatever decision rule you create, it doesn't matter how sophisticated you go. Neiman Pearson said you are going to make mistakes. And you may ask yourself, why? Why I cannot create a decision rule that never makes a mistake? Well, because you are not God, probably. But if you want a more reasonable answer, is because you are trying to say something about millions with information about from a few hundred. You have limited information. You're trying to say something about a population, but you only have information of a sample. And if you're trying to make decisions based on limited information, now and then you're going to make a mistake. It's quite reasonable. Now, they identified two types of mistakes. So here we have reality in this table over here. And here you have your decision rule. That's your test. Now, in reality, you have two possibilities. The null is true or the null is false. You don't have any other possibility. And your decision rule will deliver two possible outcomes. You reject the null or you do not reject the null. So you can consider these 4x4 table, these 2x2 tables that give you four possible options. You may, for instance, you may reject the null when the null is not true. You may be over here. So here, the null hypothesis is not true, and you did the right thing, you reject it. Or maybe the null hypothesis is actually true, and then you do not reject it. That's also a correct decision. And ideally, you would like always to be in this diagonal. That would be paradise. You will never make a mistake. But that's pretty unrealistic. So sometimes you're going to make mistakes, and there are two possibilities. Maybe the null is true. There is nothing going on. Remember, the null hypothesis is constructed in a way that is always the null effect, nothing going on, no association, nothing. Maybe there is nothing going on, but you made the wrong decision. You reject the null. So this is a mistake, and we call that type 1 error. A type 1 error is a false discovery. There is nothing going on, but you're going to claim that there is something happening. And you're going to write a paper and you're going to publish in a scientific journal saying, I have discovered something, when actually there was nothing going on. That's called type 1 error. But there is another possibility. Maybe the null is not true. Maybe there is something going on, but you are not going to reject the null. Based on your data, you are going to miss the opportunity of discovering something. And we call that type 2 error. So a type 1 error is a false discovery. A type 2 error is a discovery that you miss, right? And these are the two main errors that you can commit. And now the idea is, how can I construct a test so that I somehow take into account these errors? I keep them under control. So we want to construct this critical region. I'm going to see my outcome in my experiment, my data set. If it is in the critical region, I will reject. If it is not in the critical region, I will not reject. But I want to construct this critical region in such a way that somehow I keep these errors under control. I cannot avoid them. Now, I'm going to make a mistake now and then, but that somehow the probability of making these mistakes is under control. So type 1 error is you reject the null, but the null is true. Type 2 error is you do not reject the null, but actually you have done it. So a false discovery, here you have a discovery that you miss. These are the two main errors that we can make in research. Now, in science, we tend to give more value or get more worried about a type 1 error than a type 2 error. And you may ask, why is that the case? Well, as I said, a type 1 error is a false discovery. There is nothing going on, and you're going to claim that there is something going on. You're going to write a paper. You're going to publish in a scientific journal your results. Now, if you think about how science functions, how science is done, is kind of, we build up on the results of each other. So when I see a paper published in a journal and somebody has proven something, I just assume that that's correct, and I may use that results in my own research. Now, imagine what could happen if we have our scientific journals full of type 1 errors, false discovery. The whole edifice will collapse because we will start just using results from other people that are just false discoveries. That will be a very bad situation. And that's the reason why we try to give priority to the type 1 error. And what I mean by that is we really want to minimize that possibility. And what if there is a discovery that I miss? Well, that's bad, but probably other people are also researching that domain. Maybe somebody else will see it, but we definitely do not want to have our journals full of mistakes. So typically what you do is you try to construct that decision rule, that critical region, in such a way that the probability of a type 1 error, the probability of a false discovery is controlled. So you try to construct that decision rule so that the probability of rejecting the null, when actually the null is true, that probability is not that large. We call that alpha. And alpha is called the probability of a type 1 error, is called the significance of the test, is called the size of the test. There are different names for it. But we want to construct this decision rule, this critical region, in such a way that that probability stays low. And that's the idea. So here you have a more formal definition of significance of a test, of the size of a test. The probability of a type 1 error is the size of the test. This is conventionally denoted by alpha, is typically also called significance level, and in practice, we typically choose 5%. Alpha is 0.05. Now, this is not a dogma. This is not written on a stone. You may use another alpha level. It has become a kind of convention to use a 5% for type 1 error probability, but you can consider other values as well. So what is the alpha? Alpha is the probability of rejecting the null, the probability that your data are going to fall into this critical region when actually the null is true. If this is the situation, if I collect my data and I see my data in my critical region and I reject the null, but actually the null was true, I want that to happen with a very low probability. How low? Typically we choose 5%. Why they call it the size of the test? Because this probability here actually measures how big is going to be this region if the null is true. That's a way you can interpret it. Now, another important concept is the concept of power of a test, which is very much related to the type 2 error when we are dealing with this. What is the power of a test? What do we call by power of a test? Well, the power of a test is a probability. Again, the type 1 error and the power are both probabilities. The power of a test is the probability that the test will correctly reject the null when the null is false. So actually is the probability of that your data will fall into the critical region. So you're going to reject the null when actually the null is wrong. So when the alternative is true. And that is called the power of the test. If you want, the power is the capacity of the test to detect, the capacity of the test to detect a difference, because the null always means no difference, no association, null effect. So it's the capacity of the test to detect a difference, to detect an association, to detect that something is going on. That's the power of the test. And then, of course, 1 minus the power is the probability of a type 1 error. So it's the chance that there will be something going on, but you will miss it all together. And that's the type 1 error. Now, Frequently, the alternative hypothesis over here, what we have over here, the alternative hypothesis is composite. So typically, as I told you, the alternative hypothesis is something like, well, theta is different from theta zero. You have this type of alternative, theta zero. For instance, in regression models, what we are going to see later on in GLM, typically you want to know if a variable has an effect, the null hypothesis beta equal to zero, the alternative hypothesis beta different from zero. So the alternative is frequently composite. And that means that this power function over here, this power function is actually a function indeed of the parameters. So in this case, the power is a function of the value of the parameter under the alternative. So for instance, if you say theta different from theta zero, let's assume that this is just zero over here. So if you're saying theta is different from zero, well, theta can be -1, can be -10, can be 10. So the power of the test will be the probability that you will reject the null if theta is equal to -1. What is the probability? The null is theta equal to 0. And then what is the probability that you will reject the null if theta is equal to 25, which is different from 0? So now your power becomes a function of theta. And when theta is equal to 0 exactly, then what you get is the type 1 error, is the alpha. But when theta goes further and further from 0, the probability that you detect that difference varies as a function of theta. And that is called the power of the test. There are a couple of other concepts I want to give you because you may find it in the literature. One is the concept of consistency for the test. Now, the previous time we saw when an estimator is consistent. You remember what was that? Well, an estimator is consistent basically if when you have enough information, it gets so close as you want to the true value you're trying to estimate. So a consistent estimator has this very nice property. Essentially, if you have a consistent estimator of a parameter, you can get as close to the true as you want. The only thing you need is enough data. And consistency, unlike unbiasedness, is not such a debatable property. We all want to have that. So the more information I have, the more precise my conclusions. I can get as close to the true as I want. I just may need a lot of data, but in principle, I can get so close to the true as I want. That's a consistent estimator. What is a consistent test? Well, the power test is a function of the sample size. So typically, the larger your sample size, the larger your power. And a test is called consistent if the power of the test goes to 1 when the sample size goes to infinity for whatever value of the alternative. So suppose that you have a regression model and the null hypothesis is beta equal to 0 and the alternative hypothesis is beta different from 0. And you have a test for this hypothesis. Now, under the alternative, beta can be whatever. It cannot be 0, but it can be minus 0.3, can be 10.5, can be under the alternative, beta can be whatever. Now, choose whatever value there under the alternative. Choose beta equal to 5, for instance. Well, if your sample size is large enough, you are going to detect that beta is different from 0, that is 5 actually, with a certainty, with a probability of equal to 1. So no matter how you deviate from the null hypothesis, if you deviate, maybe just a little bit, but you deviate and your test is consistent, then if the sample is large enough, you're going to detect whatever deviation. So a consistent test is like a consistent estimator. You are always going to detect that the null is wrong if it is actually wrong. Doesn't matter if it's just a little bit wrong. If beta instead of 0 is 0.003, it's almost 0, but it's different from 0. Well, if your test is consistent, you will be able to detect that, to see that. You may need a huge sample size, but you will be able to detect that because your test is consistent. The power will go to 1. Whatever deviation you have, the power will always go to 1 if you have enough information. That's a consistent test. And then there is another important concept here that is called the most powerful test. What is that? Well, suppose that you have a test. We're going to call it A, just to use some notation. You say that this test is uniformly most powerful. We call it UMP. If it has has greater power than any other test of the same site for all admissible values of the parameter. What that means? Well, you have two tests. You have test A, and you have choose another test, whatever it is, we're going to call it B. When we are going to say that A is UMP, so it's uniformly most powerful, both tests have the same probability of a type 1 error. You need to compare pears with pears and apples with apples. So the type 1 error we're considering for the test A is the same as the type 1 error we're considering for test B. Let's call that alpha. Well, whatever value of theta in the alternative hypothesis, so let's say that H1, the alternative hypothesis is theta different from 0, just to make it more concrete, theta different from 0. Well, for whatever value of theta there is no 0, you have a better power to detect that with test A than with test B. When you have a test A that satisfies that for whatever test B you can imagine, that is your best choice, obviously, because this test A will not make more type 1 error than the other tests because they all have level alpha, but it will have more power than all the other tests. And that's called uniformly most powerful test, UMP. The problem is that sometimes it doesn't exist. It's very difficult to find a test that outperforms all the other tests. Life can be hard sometimes. It would be nice to have them. We are going to see today an example. Sometimes we have one. And if you have that, then you don't need to have more than one test, right? If you have a testing problem and you know what is the UMP test, your job is finished. This is what you are going to use. It will be silly to use something else because that will mean that your test is going to be less powerful. I propose to do the following. I propose that we continue, and then at the end, we can answer all the questions. I think it's going to be easier that way. Okay, so write it down, please, and at the end, we will discuss it. So that's the most uniform powerful test. Well, let's go back to our sample, our birth weighted sample. We had a data set with 30 babies. So we have a sample. X1 is the birth weight for baby 1. We have it for baby 2, and we have it for baby number 30. And we know that this sample, we are assuming, and we saw it in the previous class, we saw this histogram of birth weight, it really follows a normal distribution. So these data are being generated by an underlying data generating mechanism. This may be very complicated, and it may depend on genetic factors, what the mother is eating, she's doing a sport, the environment. This guy thinks that in Limburg, the environment is, there is more nature, the air is cleaner, people live at a lower speed. He thinks that all that, this complex mechanism that produce these outcomes, we are going to assume that it can be modeled by a normal distribution. And apparently it is well so. That's what the empirical evidence is. And here we have the average birth weight in Limburg. We are going to call it mu-L. And of course, there is also variability in the data. We're going to call that sigma-L, the standard deviation. Even if you only consider Limburg, or not all babies are equal. There's biological variability there. And now we can construct something called the z-scores. What is the z-scores? You calculate the sample mean minus the mean of the sample mean. In this case, if the observation has mean mu-L, the sample mean has also mean mu-L. And you divide it by the standard deviation of the sample mean. And the standard deviation of the sample mean is the standard deviation of the variables divided by the root square of n. That's a very basic mathematical operation. And we know that z-scores follow a normal distribution. Why it follows a normal distribution? Well, the x's are normal, so the sample mean is also normal, and then when you subtract the mean and you divide by the standard deviation, then what the result is that this variable here follows a normal distribution with mean 0 over here and a standard deviation 1. That's a property of the z-scores. Now, there is a problem here. We are trying to construct here the test statistics, because when we have the test statistics, we can construct the critical region. But there is a problem. And the problem is that the sigma-L over here is unknown. So the mean is unknown, but we want to make inferences about the mean. But there is another unknown quantity in our statistics, in our set statistic, which is the sigma-L. This is unknown. It is unknown, but we have data, right? So we can estimate it using just the sample standard deviation. So we can use the data to estimate that. And then instead of working with the so-called z-scores, we will work with the t-score. So what we are doing is we are plugging in here. We are plugging in here the estimate of the standard deviation. That's simply what we are doing. Now, the z-scores follows a normal distribution, but the t-scores, what distribution that follows? And that was determined by a mathematician, a statistician, William Gossett, That's the one that created the famous t-test, William Gossett, and he published under the pseudonym of a student. That was so because he was working in a beer factory, the Guinness Beer Factory. I have the chance to be there, and his research was considered classified. It was really classified information, so he couldn't publish it. But as a good scientist, he wanted to publish his results. He wanted to put it out there for other scientists to use it. So he started publishing his results using a pseudonym, a student. And that's why we call it, you sometimes will talk about it as the student test. And so what he found out is that if you have variables that are normally distributed, like the birth weight we have, but you don't know the standard deviation of these variables. The mean is unknown, but also the standard deviation is unknown. And you construct the t-scores like we did before. So you just use the sample standard deviation to estimate sigma here. He found out that this guy over here is not normally distributed anymore. If the standard deviation is known, if this is known, then you get a set score, and that's normally distributed. But if you have to estimate it, then it's not anymore normally distributed. But he found out the distribution this follows. It follows something called the t-distribution. And this t-distribution depends on one parameter that is called the degrees of freedom. And in this case, if you are just testing that the mean is equal to a constant, like we are doing, the degrees of freedom of the t-distribution would be n minus 1 when n is the sample size. He developed that theoretically. And here you have the normal distribution. This over here is the black line is a normal distribution. Now what we are going to do now is we're going to plot these t-distributions for different degrees of freedom. Here you have, this is the t-distribution if you have 1 degrees of freedom. As you can see, the tails here are a lot thicker than the normal. The normal goes to 0 faster. Here you have when you have 2 degrees of freedom. That would be a sample size of 2. When you have 8 degrees of freedoms, we have 30 degrees of freedom. As you can see, it gets closer and closer to the normal when the degrees of freedoms increases. But now, that's quite of kind of logical. Why? Think about it. The degrees of freedom is the sample size minus 1. So if the degrees of freedom are very large, essentially what you have is a large sample size. And if you have a large sample size, your sample standard deviation is going to get very close to the true standard deviation because it's consistent. It's the property we saw before. So it's going to be so close to the true that you can almost ignore that this is an estimate. You can just think, well, this is the true value because you have gotten very close to the true. And that's why the t-distribution kind of gets closer and closer to the t-distribution, so the normal distribution. Now remember, the normal distribution, the t-distribution, these are theoretical models, something we humans have created to make sense of data. And if your x is normal and you construct these t-scores, in the case of birth weight, we know it's normal. The normal is a good model there. Well, if you have a normal outcome and you construct the t-score, then these t-scores are going to follow t-distribution. That's what William Gossett proved. So let's go on. Here we have our t-score, and we know this guy is coming from a t-distribution. Why? Because the birth weight is normal. Birth weight is normal, and we know that when birth weight is normal, then the t-score follows a normal distribution. What about if birth weight is not normal? Well, the t-score will still be t-distributed, but then you will need a large sample size, You need to go to asymptotopia, the land of the big samples. Okay, now I have my t-statistics, and I know that if the null hypothesis is true, under the null, this is going, well, not under the null. Here you have a general mu L. So let's go. Here I have my t-statistics. And how can I use that now to construct my critical region? Well, the critical region are all the outcomes, all the possible outcomes of my experiment that satisfies that the absolute value of this t-score is greater than c. Why we use the absolute value? Well, because look at the alternative hypothesis here is what we call two-sided. It can be smaller than 3.3, it can be larger than 3.3. So any deviation to the left or to the right needs to give evidence against the null. We need to take that into account. If this goes too much to the right, to this side of the distribution, or this goes too much to this right, both are going to indicate evidence under the null because the null says exactly that it's 3,3, which by the way is going to coincide with the average of 0 for the t-score. But let's go step by step. So here I have my critical region. The only thing I need to do is to calculate this C in a clever way. And how we are going to do that? What it means to calculate it in a clever way? Well, what is what I want? I want to keep under control the type 1 error, right? I don't want to go there saying that Limbus is special and everybody start moving to Limbus when actually there is nothing going on, right? So I'm going to reject the null if this statistics is greater than C. That's my critical region. And I want that this is going to happen very infrequently if the null is true. So I need to calculate, I want this to happen with a very small probability. This over here should happen with a very small probability under the null when mu L is 3.3. Why? Because that will be a false discovery. And in science, we are very worried about it. So I want to calculate this C in such a way that this probability of type 1 error stays low. And low is alpha. And alpha is typically 0.05. So I want to calculate this C in such a way that the probability that I will reject if the null is true is going to be 5%. And now you can use, because under the null, if this is true, this guy follows a t-distribution, right? And then you just can calculate the necessary C for that. When you come here, well, the probability that this will be, the absolute value of t will be larger than C, well, you need to find for which values is going to be larger than C or smaller than minus C. You need to calculate who is that C, larger than C or smaller than minus C. And the C has to be chosen so that this stays 0.05. And when you do that, then you can calculate that the C unit is 2.04. And this is your critical region now. Now you can repeat this experiment again and again and again, and you will get different data sets, different set of 30 measurements. The only thing you need to do is to give me your data. I will come here and I will see if your data fall into the critical region W, or the rejection region. So the only thing I need to check is that your data satisfies this inequality. If it does, then you can reject the null. You have found something. There is something different in Limber. If it doesn't satisfy that inequality, then we don't have evidence that there is anything special going on. And that is the procedure of Neyman and Pearson. No p-values, no borderline p-values, something like that. Use reject, do not reject. Reject, do not reject. It's an algorithm that has two possible outcomes. I will reject or I will not reject. That's it. That's everything. And that is the paradigm of Neyman Pearson. It's an algorithm, it's a decision rule that allows you to reject or do not reject the null. And it's a good decision rule. Why do you mean by good? Well, it doesn't make too many false discoveries. If you repeat your experiment again and again and again, and you use this algorithm to decide, you are going to make a false discovery only 5% of the time. So if there is nothing going on, if Limber is just like all the rest, and you repeat this experiment 100 times, and you use this algorithm 100 times, only 5 times you are going to end up claiming that something is going on, when actually nothing is going on. So I'm satisfied with this type of procedure. And this is the mindset of Frequentis statistics. That's what the Frequentis school does. We create methods and we decide if they are good or bad by doing this kind of mental simulation. So if I repeat my study again and again and again, I'm going to construct this method so that it works fine most of the time. Now, suppose that you have a data set, like we have here, a concrete data set. Let's do it. We have a concrete data set. So under the null, mu is 3.3. We can estimate this using the sample. And then here we get our absolute value is 1.78. And that 1.78 is smaller than 2.02. So it is not in our critical region. Conclusion, no reject. That's it, period. We don't talk about, in the Neyman-Pearson paradigm, we don't talk about anything else. And for some time, there was a debate between Fisher with his p-values and Neyman-Pearson with their critical region. And as you will see, we end up kind of mixing both. But that's it, do not reject. Now, you may say, are you sure this is not a type 1 error? I mean, maybe there is something in Limber and I just failed to detect it, right? It may, sorry, maybe there is nothing going on in Limber and I just, well, this is not a type, here we did not reject, but suppose that we reject and you say, are you sure you have not made a type 1 error? And the answer there is, no, I'm not sure. If you reject, you can never be sure that you're not making a type 1 error. But I'm not so worried. Why? Because I'm using a procedure that doesn't make too many type 1 errors. So I believe that has worked fine now too. In this case, it's different because we did not reject. So we may be committing a type 2 error, but not a type 1 error. But that's the philosophy. We evaluate the procedures in these mental simulations. Now, that's critical region. That was the paradigm introduced in the 1930s by Neiman and Pearson, and has become to a certain degree the dominant paradigm when we test hypotheses. We construct critical regions, we reject, we do not reject, period. Now, if you do a statistic, you probably use software for that. We don't do it by hand, right? Not anymore. And software typically, what they use the other tool. Softwares, they typically use p-values. They don't use critical regions, they use p-values, even though there is some relationship between these two concepts, and that's why people kind of mix them up. What is a p-value? Well, a p-value is the first, it came first than the critical region paradigm of Neiman Pearson and was proposed by Fisher. So Neiman and Pearson, they saw hypothesis testing as a decision rule. You reject, you don't reject, period. Fisher had a different idea. Even Fisher didn't consider an alternative hypothesis. He says we just have one null hypothesis, and I want to quantify the compatibility between the data and the null. How can I get that in a number? How can I calculate a number that quantifies the compatibility between the data and the hypothesis I'm trying to test? So he didn't think in terms of type 1 errors and type 2 errors and power. He didn't have that mindset. He just said, I have data, and for Fisher, it didn't make so much sense to start thinking about repeating the experiment theoretically in your mind many times. It doesn't make any sense. I just have one data and one data set. And what I want to do is I want to quantify the compatibility between that specific data set and my null hypothesis. That's it. That was what Fisher was trying to do. And he created a number for that. It's the p-value. Neiman and Pearson had a different idea. No p-value said, this is a kind of rule, and I want my rule to work fine most of the time. And how I'm going to evaluate that, I'm going to do these mental simulations, and then I'm going to do theoretical calculations to make sure that my rule will satisfy this frequentist property. Fisher follows a different path. What he said, well, I have my t-statistic here. He was also using the t-scores. And he said, well, I going to calculate that t-statistics with the data. So you just put here the sample standard deviation. Under the null, the mean is 3.3 like we have here, and you calculate the absolute value of that. Now, why we are doing that? Because Fisher said, well, this t-score has a property. If the null hypothesis is true, then the mean is actually 3.3, right? And then the numerator here, over here, should be close to 0 because the sample mean is going to have the same mean as the outcomes. And if the outcomes under the null have a mean 3.3, then the sample mean is also going to have mean 3.3. So this is going to be very small over here. So if the null is true, that t-statistic should be close to 0. It should be around here, maybe a little bit less, maybe a little bit more, but should be close to 0. If you get a value very far from 0, to the right or to the left, that is giving you evidence against the null. So we calculate the absolute value of t. In this case was 1.78. And if this is very large, that means that the t-score is or too much to the right or too much to the left. And that means I have evidence against the null. Because if the null is true, this value should be around here, should be around 0. So large values of absolute value of t, a large value for the absolute value of the t-statistics, the test statistics, that gives evidence against the null. Okay, we got 1.78. Is that too large? Well, that's a good question. How we quantify that? Because if it's too large, then we get evidence against the null. Now imagine for a second, I mean, you have never seen me, but I'm 170. 172, if I'm a little bit optimistic. And imagine if I ask you, well, am I tall, right? Well, probably you would say, well, the first thing is tall where? Because it depends on the country you are, right? In my own country, I'm kind of average. Now, but they say, well, in Belgium, am I tall? Well, probably if you look at me and say, he's 170, no, he's not. And why you could say that? Well, there are many ways you can formulate your argument here, But the one way is because the probability I can see somebody taller than you is very large. I mean, if I go to the street and I look around, I will find a lot of guys taller than you. So you don't look that tall here because the probability of observing something taller is large. And that's the principle of p-value. Is 1.78 too large? Well, I'm going to calculate the probability of observing something larger if the null hypothesis is true. So what is the probability? If there is nothing going on and the null is true, what is the probability that I can see something larger than 1.78? And that probability is, in this case, 0.08. And that's what we call p-value. So if the null is true, the probability that I can observe something extremer than 1.78 is 0.8. And we consider, and this is again a kind of convention, it's not a dogma, that the probability is small if it is smaller than 0.05. So if the probability is smaller than 0.05, we claim that it's a small probability. And in this case, it's not. It's larger than 0.05. So we say, well, you know what? 0.78 is not that large because 8% of the experiments will lead to a value larger than 1.78. So it's not, if the null were 2 and there was nothing going on, I will still see a lot of results that are more extreme than 1.78. So that's not that large. So the data and the hypothesis are kind of compatible. The data are not so weird. If the null hypothesis were true, this data would not be that strange. We could observe something like that or even more extreme. And that's what we call p-value. Now, in the case of p-values, we don't talk about type 1 error, type 2 error conceptually. We could do it, but conceptually we don't do it. What Fisher said is, well, you get a number there, and now you need to consider if that is enough evidence for you to reject the null. So you have 0.08.6% of observing something more extreme than 1.78 if the null is true. Do you consider then 1.78 extreme? Well, 8% probability of seeing something extremer, but probably is not that extreme. And then in the statistics, sometimes when you get, for instance, something like 0.051, well, it's now small enough. Then people start talking, well, yeah, you have only 5% 0.1 chances of observing something more extreme than that. Maybe that's very extreme or borderline extreme or gives some evidence against the null. You have all these considerations. In the Neyman and Pearson paradigm, you reject, you do not reject, period. Now, you can mix both approaches. You can, for instance, this is typically what we do in practice. So what people do, they get their p-values, 0.08 in this case, well, almost 0.09 in this case. And then people say, if it is smaller than 0.05, then we reject the null. We take the decision of rejecting the null. If it is larger, we do not reject. So we construct the critical region based on the p-value. Smaller than 0.05, we reject. Larger than 0.05, we do not reject. So we, instead of using the critical region to reject or do not reject, we use the p-value, and these two things are equivalent. So, but if you want to be a purist, strictly speaking, this is a little bit of mix in both ends, because Fisher will say you have the p-value, you have a number that quantifies how compatible are your data and the null, and now you analyze that. You can fix that if the p-value is smaller than 0.05, you stop there, but he didn't have in mind this idea of repeating the experiment again and again and again. So we have seen these two paradigms. They are the two main paradigms, the critical region paradigm and the p-value paradigm. However, there is another way. Well, what conclusion you take here? The p-value is 8%, almost 9%, and there is again this convention that a p-value larger than 5% is not that small. So actually 1.78 is not strong evidence against the null. Why not? Because if the null were true, you would still observe in 9% of the cases values more extreme than this. So not reason to worry about the null. So here we have, this is the kind of mixing paradigm we actually use in practice. So here you have the null hypothesis, that's that the mean has certain value, mu 0. This is can be 0, 3.3 in the study. And you have the alternative, that is that the mu have a value different from 3.3. So you have here a single hypothesis, the alternative is a composite hypothesis. And what we do is you collect data, you take a sample, you calculate your test statistics, and then you calculate based on your test statistic the p-value. If it is smaller than alpha, you reject. If it is not smaller than, if it's larger than alpha, you do not reject. And this is a kind of algorithm. And here you kind of mix up both approaches because you construct your critical region based on p-values. But this is what we do normally in practice because softwares provide only p-values. Now, this algorithm, if you apply it in the Frequentist framework again and again and again, and there is nothing going on, it will very infrequently make a type 1 error, only 5% of the time. But if you have a concrete data set and you reject, and the question is, have I made a type 1 error now for this specific data set? The answer to that is, I don't know. I don't know because the null, you don't know if the null is true or not. So in practice, you don't know. But you say, I'm not going to be very worried because this is an algorithm that if nothing is going on, he doesn't make too many type 1 errors. So I'm going to believe my results. Of course, all this is nice and work under certain assumptions. One assumption is you need that the data are normally distributed, like birth weight. If that is not the case, then you need to make sure that your sample size is large. Well, how large is large? It's like with the central limit theorem. Actually, that's what you will use if the data are not normal, the central limit theorem. Well, typically a sample size for continuous variable larger than 25 may be enough, but please be careful here. This rule of thumbs can be rather dangerous. And of course, your data need to be independent. So the birth weight of one baby has nothing to do with the birth weight of another baby. That may be not true if you have twins in the study, but let's assume that that is not the case. Okay, just a couple of general comments here. In science, it's very difficult to prove or disprove something 100% certainty, with 100% certainty. And if you have a debate between a scientist and somebody that is not a scientist, sometimes the scientists look bad because when they ask the scientist, are you absolutely sure of this? A good scientist will always answer no. Scientists are aware of the uncertainty. I always advise people when you see somebody, now with the pandemic, there is so much misinformation out there. I always say to people, if you listen to somebody and this person is absolutely sure about what he's saying, probably is not somebody you should trust. Now, another important thing is the difference between a statistical significance and practical importance. Something may be statistical significance and still be practically relevant. Suppose that you have two treatments, treatment A and treatment B. And treatment A will cure you. You will be cured in, let's say, 1 day. And with treatment B, you will be cured in 1 day and 2 hours. Now, these treatments are not the same. There is a difference of 2 hours between both of them. And if your sample size is large enough and you're using a consistent test, you are going to detect that. You're going to get a significant p-value. So your decision rule will tell you, reject these two things are not the same. Now, that is true, so it's a statistical significant, but from any practical point of view, a difference of 2 hours is absolutely relevant. So keep that in mind. Not always a significant p-value. A statistical significant result is something practically relevant. These are two different concepts. Now, when you're going to write your hypothesis, I told you the alternative hypothesis can be one-sided or two-sided. Typically, for instance, one-sided hypothesis is the effect is larger than 0 or is smaller than 0. And the two-sided hypothesis is different from 0, but it may go in both directions. Now, you should try to specify always two-sided hypothesis unless you really have good reasons to consider only one side. For instance, if you're doing a test for a variance and you want to say the null hypothesis, the variance is equal to 0, then it makes a lot of sense to consider an alternative that said the variance is larger than 0, because per definition, variances cannot be negative. By the way, if you had testing a variance equal to 0, be careful with what you're doing because 0 is at the border of the parameter space. The variance cannot go under 0, and that may bring sort of problems. But this is an example in which it makes sense to consider an alternative that is just one-sided. But if you are not sure, you should leave open the possibility that it can go both ways. Why is that important? Because one-sided test tends to reject the null faster. Why? Because you are introducing extra information. You're saying it cannot go, one of the two sides is not possible. So you're adding information to the test, and you better be right. So you better, let's hope that it's true that it can only go to one of the side. And so these are concepts that are important to keep in mind. Now, I told you that these are the most classical methods we use in hypothesis testing. We use p-values, we use critical regions. However, something that is not used frequently, and I don't know why, is to use confidence intervals, because they are a lot more informative at the end of the day. Well, the idea here is, suppose that we want to test that the birth weight, the average birth weight in Edinburgh is 3.3, that's my null or not, different from 3.3. Well, I can calculate a confidence interval. I have a sample of 30 babies. I can use that information to calculate my confidence interval, and here it is. I get a confidence interval that the average birth weight in Limburg is between 3.10 and 3.85. Now, what is the probability that the true average birth weight in Limburg lies in this interval? Well, that probability is 0 or 1. The true value is there or is not there. Oh, really? And which of the two? I don't know. Now, if you say that to a doctor, he's going to get quite shocked. You come there and say, well, the average birth weight lies between 3.10 and 3.85. Are you sure? No. What is the probability that is there? Well, it's 0 or 1. Is there or is not there? Really? And don't ask me in which of these two situations I am, because I really don't know. And actually, that's the right way of looking at it. Now, I will tell you, I'm not so worried. Don't worry so much, because this specific interval here, this 3.5, 3.10, 3.85, this specific interval over here has been produced by an algorithm, by a procedure, which is the one here. And this procedure works fine 95% of the time. So if I apply this formula 100 times, 95 times is going to contain the true value. So I hope that we're fine now for this specific data. I'm 95% confident that it has done the job well now, because it does it well most of the time. And that's the frequentist mindset. So this is a good procedure, because if I use it 100 times, it works fine 95. So now for this specific data set, I'm not that worried. Probably did the job well. It almost always does it well. Now, how can I use this interval to test the null hypothesis? So the question here is, does this sample come from a population with a mean of 3.3? That's what we want to answer. And well, I have a confidence interval for the mu L. So my interpretation of that confidence interval is that we are 95% confident that the true mu L lies somewhere between 3.10 and 3.85. 3.1 and 3.85. So it can be 3.3. It's somewhere between these two values over here and over here. So 3.3 is included in my interval. 3.3 is inside my interval. So I have no evidence to say that it cannot be 3.3. I do not reject the null. The advantage of the confidence interval is that it doesn't give you a binary answer, reject, do not reject, but it's more informative. It tells you, well, we don't have any evidence that is not 3.3. Actually, it could be somewhere between 3.1 and 3.85. We know it should not be larger than 3.85, and it should not be smaller than 3, but it could be 3.3. So it's a richer methodology. It gives you more information. Okay, we're going to start now a more dense part of the lecture. We are going to, but also a more relevant one, because we are going to start seeing now what they are called the holy trinity of inferential statistics, which are 3 tests that you can use then also to construct confidence interval that permeate all the statistical modeling, which is the Wald test, the likelihood ratio test, and the score test. And these are called the holy trinity of inferential statistics for something, and it's that these are the tests you are going to get out of most softwares. But before going into it, let's stop for a second, let's take 5 minutes, and then we will be back. Okay, let's continue. So um, we are going to study these three tests, which are very, very widely used in statistics in general. We call it the holy trinity of statistical inference. So let's assume that you have parameters. These parameters govern in your model, and we will divide this vector of parameters in two sets. One that we are going to call theta1 and one that we are going to call theta2. And we are doing this because frequently you have a model and this model has parameters, and there are some parameters that are really interesting. This is the one that you want to study, and you have this kind of nonsense parameters. For instance, if you're doing a linear regression, you're typically interested in the betas, but you have the variance there that you need to estimate to construct your test, but actually is not the objective of your research. You're interested in the vector of coefficients. That's what we are doing here, separating the parameters in theta1 and theta2. And this theta1 and theta2 are just subvectors of the whole vector of parameters, which one has dimension. If the whole vector of parameters, you have p parameters in your model, you can consider that one has dimension p minus r and the other one has dimension r. This is completely arbitrary, just a little bit of formalism. Now, you may think about hypothesis for theta, right? You may think that you want to um, uh, answer some hypothesis, to test some hypothesis. And we will consider a simple hypothesis and a composite hypothesis. Remember, a simple hypothesis completely specifies the distribution of the data. So a simple hypothesis will be when you say, well, theta is equal to certain value. Theta 0 is an unknown constant, like in the case of the birth weight, 3.3. So you may consider a hypothesis in which you say the whole vector of parameters is equal to theta, theta 0, and the alternative hypothesis, which is composite, means that theta is not equal to theta 0. And we are going to consider a composite hypothesis for the null as well. And that means that the null hypothesis will be that theta is, well, theta 2 is completely specified, is equal to certain constant, but the rest of the parameters are left without a specification. And the alternative hypothesis will be obviously given here. This is, for instance, when you have regression model and you want to test that one coefficient is equal to 0. So you may have 10 coefficients plus the variance, and then the null hypothesis is beta 1 equal to 0, but all the other parameters, you don't say anything about them. That would be an example of this type. So let's consider now some notation here. You are going to call theta hat the maximum likelihood estimator under the alternative hypothesis. So it's just when you apply the maximum likelihood estimation method, not restricting your parameters at all, like you do on the null hypothesis. We call that the unrestricted estimator. And then you are going to calculate, we call it theta 0 hat. That's the maximum likelihood estimator under the null hypothesis, right? So that is equal to theta 0 if you have a simple hypothesis. So if you want to estimate the parameters under the null, but under the null you are specifying the whole vector, then there is nothing to estimate. Under the null is theta 0. That would be the maximum likelihood, what we call the estimator under the null, would be theta 0, because the null itself specifies the entire vector. But if you are in the composite case, like we are here, then we will, under the null, estimate, still we have to estimate theta 1 over here. So we are going theta 0 head will be theta 0, the constant, if you are in this setting, or it will be theta 0, the constant you specify here, and then you will estimate theta 1 still, because under the null, this one will still be free. So we will call the estimator under the alternative just theta hat, and under the null, we will call it theta hat 0, and depending whether you are here or here, you will estimate it like just the constant, the null specified, or in this way. We will need this notation later on. Now, let's consider the score function, because to estimate the parameter, typically we use maximum likelihood, and maximum likelihood is based on the score function. Remember, the score function is the logarithm, is the derivative of the logarithm of the likelihood function. So it's the derivative of the log likelihood. Please go and watch the video of the first lecture. I covered that there. I try to explain it as clear as possible. So we are going to divide the score function into components. So we need to calculate the derivative with respect to theta of the log likelihood function, and we call it L of theta. And remember, the log likelihood function is the logarithm of the likelihood. And the likelihood is the probability of the data but you look at it as a function of theta, which is now a mathematical function. So you remember the principle of maximum likelihood. You can check it in the previous lecture, but the idea is, if we studied in the previous lecture different ways or different properties that a good estimator should have. And these properties were in the frequentist framework. For instance, I want an estimator that minimizes the mean square error. So that means that it's an estimator that the average distance between the estimator and the true is smallest. That's a possible property that you may want. But you may also want your estimator to be unbiased. And that means that if you repeat your experiment, your estimator fluctuates around the true value. Or you may want your estimator to be consistent. And that means that you can get as close as you want to the true if you have enough information. That's consistency. Or you may want your estimator to be asymptotically normal. Or you may want your estimator to be efficient so that it reaches the lower bound of the Cramer-Route inequality. All that is discussed in the first lecture. Go there. You can watch it as many times as you want. And that's fine, but then the question rises, okay, how can I find such an estimator? Because you are telling me all these nice properties that I may be interested in, but do you have a procedure to find them? Because yes, I can start guessing here and try to construct formulas based on the data, because that's essentially what an estimator is a formula of the data. And I can start creating formulas and see that it satisfies these nice properties. But can I have some kind of automatic way of producing these estimators? And one such a way is, there are different ways, that the method of moments, but one of such a ways is the maximum likelihood estimator. And this is again an idea that dates back to the beginning of the 20th century. Ronald Fisher, the genius of our field. And what he said is, well, if you need to estimate theta, and you're assuming that your observations are being generated, there is some kind of latent common underlying data generating mechanism. There is a mechanism that is generating all these observations, and this mechanism you're modeling with a probabilistic model. Now try to find the value of theta that makes your data most visible. Try to find the value of theta that makes the probability of observing that specific data largest. And why is that a good thing to do? Well, because you actually observe that data, right? So this data is not that weird. I mean, maybe it is. Maybe you have observed a miracle. Maybe it's a very rare outcome, and you just happen to observe it. Strange things happen sometimes. A low probability doesn't mean impossible. Can still happen. But I mean, that's very unlikely, right? So the idea is, I'm going to calculate the value of the parameters that give that data set I have observed the largest probability, because actually I observe it, so it should not be that weird. And this is what we call the maximum likelihood estimator. And the maximum likelihood estimators, if you have a large sample size, they are unbeatable. Small sample properties are not optimal. But if you go to Asymptopia, if you are in this land of large sample sizes, then your maximum likelihood estimators are very good. They are asymptotically unbiased, so they will fluctuate around the true value. They are asymptotically normally distributed. So you know what is the distribution of the estimator. They are efficient, so they have the minimum variance. They reach the lower bound of the Cramer-Route inequality. So if you have information enough, your maximum likelihood estimators are unbeatable. They have a set of nice properties. Asymptotic unbiasedness, they are efficient, asymptotically normal, consistent, so they will get closer and closer to the truth. You can get them as close as the truth as you want if you have enough data. So they have very nice properties. And the only thing we needed to specify then is, okay, how you calculate them. You need to maximize this likelihood. You don't work typically with the likelihood, but with the log likelihood, because the log likelihood makes a product a sum, and sums are more tractable mathematically. And what you do is you need to calculate the maximum of a function, and this is something you do by calculating the zeros or the roots of the score function. So what you do is you calculate the first derivative of the log likelihood. This is what we call the score function over here. You equal that to 0, and you solve the problem. And that may be your maximum likelihood, maybe also minimum of the log likelihood. That's why you need the information matrix. But let's stop here for a second. So you need to calculate this derivative over here, and you're going theta. Remember, theta is theta 1 and theta 2. So You put here first the derivatives with respect to theta 1, and you put here later the derivatives with respect to theta 2. That's what we are doing here. You're decomposing the score function in the derivatives with respect to these two subvectors we are considering. And then you have the information matrix. We talk about that, the Fisher information matrix, which is the minus the expected value of the Hessian. Go to the first lecture. I completed it again. You can find all the information there. And then you decompose this matrix again in 4 components, as you can see here. The first part will be the one for associated with theta 1. The second will be the one associated with theta 2, and then the cross product over here. And remember, what is the Hessian? Well, the Hessian is the second derivative of the log likelihood. Let me rectify that. The Hessian is the second derivative of the log likelihood with respect to the parameters. So you derivate with respect to theta, you derivate against with respect to theta, the log likelihood. And that is called the Hessian, and it's a matrix. It's a matrix. Or if you want, you derivate again, you derivate the score function against theta again. And that will give you this matrix over here. Now, the important thing about this matrix, the Fisher information, is that it will give you the variance, covariance matrix of the maximum likelihood estimators. That's discussed at the end of the previous lecture, because actually the variance covariance matrix of the maximum likelihood is the inverse of the Fisher information matrix. And you can show that asymptotically that's the best that you can do. So you decompose it in this way over here, or you can, just for notation, you calculate the inverse, and the inverse of the Fisher information matrix, which is just the variance covariance matrix of the maximum likelihood estimator, can be decomposed in these 4 parts as well. A little bit of notation. I don't pretend that you understand all the little mathematical details. You don't need to, you probably don't know how the electricity of your car works until the very small details. However, you can drive, right? But it's good to have an idea about how that functions, especially if you're, a professional runner of cars or something like that. It's what we are trying to do here. You don't need to understand every little mathematical detail, but it's good to get some kind of conceptual understanding. And then here we have the 3 significant tests we are going to use. These are the so-called the Holy Trinity differential statistic. We have the likelihood ratio test, we have the Wald test, and we have the score test. And we are going to study them. We're going to see what their properties, when one is better than the other one. Will they always get the same result? Can I get different results, etc.? And they can be, there's some similarities, but there are also some important differences. Now, what is the likelihood ratio test? Essentially, the likelihood ratio test compares 2 models, a model under the null and a model under the alternative. So the likelihood ratio test compares 2 models. And so you compare what is the goodness of fit of 2 statistical models. How good fit the data a model that under the null, and how good fit the data a model under the alternative. And this is the way you decide if you accept or you reject the null hypothesis. Now, the Wald test tries to approach the problem in a different way. It assesses the null hypothesis based on the square difference between the estimated parameters. You calculate the maximum likelihood estimator, and you compare that with what the null specifies for the parameter. You calculate the distance. And if the estimator is very far from what the null specifies, then you will reject the null. Of course, you need to take into account the variability in your estimator, because your estimator has sampling variability. So you need to take into account, we call the curvature of the likelihood. We will see the details later. But the likelihood ratio test does, you see how is the goodness of fit of the model under the null, how good it is the goodness of fit of the model of the alternative, so how you see which of these 2 models, fit the data best. And that's the way you decide. The Wald test does it different. You estimate the parameters, and you calculate the distance between the estimated parameters and the value the nulls specify. Are these 2 things very far? Yes, then you reject the null. And the score test does it still in a different way. The score test said, well, when you calculate the maximum likelihood, so you're calculating the value of the parameters that maximize the likelihood. That is the value of the parameters that made the data most probable, right? You calculate that. Now, it is a maximum. So on this maximum value, the score is equal to 0. How do you calculate the maximum likelihood? You solve the score equation. The score is equal to 0. So on the maximum, the score function is 0. And what you do now is the following. Let's take the score function and let's evaluate it in the value of the parameters that the null specify. If this is close to 0, that means that what the null specifies is very close to the maximum. So what the null specify makes the probability of the data large. So we do not reject it. if the score function evaluated on the value specified by the null is very different from 0, what that means that what the null is saying, what the null is specifying, is very far from the maximum of the likelihood. And that means that value that the null specifies doesn't make my data very likely, and then you reject. This is the conceptual framework from this test. The rest is mathematics. That's why I said what I want is that you kind of understand the conceptual framework. So the likelihood ratio test, what you do? Well, you calculate the likelihood. This is the log likelihood, and you evaluate it in the maximum likelihood estimator under the null. You remember we specified this. This is the maximum likelihood you calculate under the null, and this is the maximum likelihood parameter, maximum likelihood estimator under the alternative. So let's repeat that again. Here you have the log likelihood, and you evaluate the log likelihood first when you on the maximum likelihood estimator of the parameters under the null. If the null is a simple hypothesis, then this is just the value theta 0 that the null specify. And you compare that with the log likelihood, but now evaluated in the maximum likelihood estimator of the parameters calculated under the alternative. And that will tell you if the difference in goodness of fit between these two models. Now, if the null is true, this statistic here follows a chi-square distribution, and the degrees of freedom is the number of parameters under the null, under the full model, minus the number of parameters under the null model. And if this is very, very different, then that means that, you know, the log likelihood varies a lot under the null and under the alternative. Obviously, the log likelihood is going to be always larger under the alternative, because you have more parameters under the alternative. So you are really evaluating the likelihood in the maximum. So this is going to be always larger than this. So this is going to be always negative. So when you multiply it by -2, you make it positive. Now, if this is very, very large, what you're saying is, you know, the log likelihood is a lot larger under the alternative than under the null. So the data are a lot more probable here than here, so you reject the null. That's what you're doing. And this is the likelihood ratio test. Now, what is the wall? Well, now let me tell you something that I told you about this uniform most powerful test, UMP. And if you have such a test, you should not create any other. Here we're discussing 3 tests. We're discussing the likelihood, we're discussing the wall, we're discussing the scores. There are many, many tests out there. But if you had a testing problem, and in that testing problem you have a UMP test, full stop, you got it. Any other test would do worse, right? Now, I told you that the problem with that is that these tests are really very rare. So in many situations, you don't have them. They don't exist. Now, there is a situation in which you do have a UMP test. And this was proven theoretically by Neyman and Pearson. It's called the Neyman-Pearson lemma. Suppose that you want to test 2 simple hypotheses. So the null says that theta is equal to theta 0, and the alternative says that theta is equal to theta 1. In that case, there is a UMP test. And what is that? It's the likelihood ratio test, the one we just saw before, well, equivalently to that. So you construct your critical region in this case, in this way. This is the likelihood function evaluated in theta 0 divided by the likelihood function evaluated in theta 1. And the critical region is if this value here is smaller than C, you reject. Because in principle, what does that mean? Well, if the likelihood under the alternative hypothesis is what you have here in the denominator is much larger than the likelihood under the null hypothesis, that just means that the data are much more likely under the alternative than under the null. So you will reject the null. And that's the intuitive idea behind the test. The only thing you need is you need to select this C in a clever way, and we do that just by making sure that the probability of a type 1 error stay equal to alpha. So you need to determine, you know that this will follow asymptotically chi-square distribution, or if you have an exact distribution, even better, and then you calculate the C just to make sure that the type 1 error stay under control. And this, if this is the problem you're trying to solve, then the likelihood ratio test is your best option because it's UMP. If you go to use something else, you're going to be losing power. But of course, this is a very simple example. And in real life, the hypotheses you're testing are typically more complex than just 2 simple hypotheses. So the null is simple, but the alternative is simple as well. You don't have that so much in practice. But if you are interested in something like that, then the likelihood ratio test is unbeatable. Now, let's go to the more general situation. So the likelihood ratio test, we saw it there, is just you calculate the log likelihood, you evaluate it on the maximum likelihood under the null, you calculate the log likelihood, you evaluate it on the maximum likelihood estimator under the alternative, and you calculate the difference between these two things. And essentially, that's the low likelihood test, and will tell you which version, the null or the alternative, fits best the data. The second one is the Wald test. And what the Wald test does is what I told you. You calculate the difference between the value that the null specifies and the maximum likelihood estimator. That's what you do. That's the distance. You calculate the distance between the value that maximizes the likelihood, that's the value that makes your data most likely, and you compare that value with the value of the null. You compare this theta hat, this maximum likelihood estimator, with theta null. And if that distance is very large, so if the theta null is very far from the maximum likelihood, then you will reject the null. Now, you measure the distance using this kind of Mahalanobis distance. You take into account the variability of the maximum likelihood, because the maximum likelihood estimator has certain variabilities. It's not the true value. And that variability is given by the inverse of the Fisher information matrix. So you correct for that. I mean, if you want to have an idea, intuition of why we need to do that, suppose, so you have here the likelihood. Let's suppose that your likelihood is like this. And here you have the maximum likelihood. This is theta hat. And here you have your theta null. And what you're doing is, here is theta null. You are calculating the distance between these two guys. Now, this situation, you see that the likelihood is rather flat. Now, this distance is different if you have a situation like this. If you have, wait, let me just consider this in a different way. If you have a situation like this, in which you have a very steep likelihood, then you have the value of theta 0 here, and you have the value of the maximum here. And as you can see, even though the distance may be more or less the same as before, now these 2 points in the likelihood will be very different, just because the curvature is higher. And that's why you need to take this into account. You need to take into account the variability in these estimates when you compare it with theta 0. And that's the maximum likelihood test. Now, this is for a single hypothesis. If you have a composite hypothesis, then you do the same. In the composite hypothesis, this is the value. You specified in the null the value of this theta 2. The value of theta 1 is left free, but theta 2 gets specified. So the Wald test, what it does, well, it calculates the maximum likelihood. This is the maximum likelihood under the alternative. And now you take this second component here, and you compare it with what the null specifies, right? The distance between what is the theta 2 head that maximizes the likelihood when you take it from here, and you compare it with the value specified by the null. And then again, you correct by variability in your estimate. And this is for the composite hypothesis over here. In any case, whether you're dealing with a simple hypothesis, you're dealing with a composite hypothesis, under the null, the Wald test follows a chi-square distribution with the same degrees of freedom. And for the score test, is a little bit of the same situation. So what you do is what we said. If the null, the value specified by the null theta 0 is very close to the maximum likelihood, to the maximum of the likelihood function, then the score test should be close to 0. So what you want to calculate is the distance between the value of the score test evaluated in theta 0, which is what the null says, and 0. This is what you want. So it is like a Wald test, but now applied to the score test. And okay, the 0, you don't need it. That's why you only have the score test evaluating theta 0 here. And again, you need to account by the variance of the score test. We saw it in the previous lecture. You can go there and have a look at it. The inverse of the variance of the score test is just the covariance of the score test is the Fisher information matrix. So you account for that here. And this is another way of testing the null hypothesis. And for a composite hypothesis, is very similar to what we saw before. You do that, but now you apply it to the theta 2 component. And you evaluate in the estimator under the null. And if the null is true, the score test is again chi-square distributed with the same degrees of freedom. So they are all chi-square distributed with the same degrees of freedom if the null is true. And these are the 3 ways you can use to assess null hypothesis. Now, the only thing you need to apply these methods is you need to be using likelihood theory. So you have your data set, you have your outcomes, you assume that these outcomes are being generated by a underlying probabilistic mechanism that is common to all the outcomes. So all these outcomes are being generated by an underlying probabilistic model that depends on theta. And now you can use that assumption to just apply likelihood theory. So you can calculate the maximum likelihood. You can, this asymptotically, this maximum likelihood estimator is unbeatable. And because it's efficient, it's consistent, it's unbiased, it's normally distributed, etc. And now you can use the likelihood to calculate the score test. If you're interested in this kind of test, theta equal to theta zero, theta equal different from theta zero, or you're interested in a composite hypothesis, some components of theta may be zero, the others are allowed to vary freely. So now you can use the score test, you can use the maximum the likelihood ratio test, or you can use just the Wald test. Now, the three statistics, the Wald test, the likelihood ratio test of the score test, are asymptotically equivalent. What we mean by that is that they all have the same sampling distribution under the null. We saw that if the null is true, the three of them follows a chi-square distribution with the same degrees of freedom. So if the null is true, they all have the same asymptotic distribution. They are going to give approximately the same p-values if the null is true. They are equivalent onto the null. Note that there are some important differences between them. For instance, the Wald test is based only on the maximum likelihood estimator under the alternative and the curvature. The score test depends on the slope of the curvature. You need to calculate the first derivative of the likelihood, and you're going to evaluate it in theta zero. And the likelihood ratio test use information under both the alternative and the null hypothesis. Now, as I said, the difference between them is going to vanish if the null is true, because they all have the same distribution. They will behave exactly the same way, or very similar way. Now, if the null is false, they may take very different values, of course. They are equivalent under the null, not under the alternative. But in that case, you will probably have that all of them will lead to highly significant p-values when the alternative hypothesis is true. Now, here you have a visual representation of the three tests. So here you have the likelihood, is this curve over here. Here you have the maximum of the likelihood. When you reach that, well, with the maximum likelihood estimator, there you reach the maximum. And here you have the value specified by the null. The null says that theta is theta zero, right? And you want to test that null. Is theta actually equal to theta zero? The three procedures follow different paths. The maximum likelihood said, okay, you calculate how much is the likelihood of the data based on theta zero. And you know what is the likelihood of the data based on the maximum likelihood. If this difference is too big, then you reject the null. Why? Because the data will be a lot less likely under the null than under the alternative. That's the likelihood ratio test. What does the Wald test does? The Wald test says, well, the null is over here. The null says that theta is over here. And the alternative says, well, if I maximize the likelihood under the alternative, I get this maximum likelihood value. Are these two guys very far from each other? If they are very far, then again, I'm going to reject the null. Because when I estimate the parameters, I get something very far from the null. Now, you calculate that distance taking into account the curvature of the likelihood, the variability in this guy, because this guy has variabilities based on a sample. That's the Wald test. And the score test says, well, the null says that theta zero is over here. That's what the null says. Theta zero is over here. Now, the maximum likelihood is over here. This is the value that maximizes the likelihood. Now, on the maximum, the tangent is parallel to the axis. The score test is the score function is zero when you're evaluating like that, because on the maximum, the tangent to the likelihood is parallel to the axis, has slope zero. Now the null says that theta is here. Well, I'm going to calculate the tangent here, and I'm going to see, because this tangent should have a slope zero if theta zero is close to the maximum. And if it is not zero, if it is very far from zero, if the score test is very far from zero, so that means that I'm very far from the maximum. So I'm going to reject the null. So you can think of this test in the following way. This is a mountain. The likelihood is just a mountain. It's a hill. And you want to know how far is this point from this point. The score test is like if you stand here in the mountain and you just look above, and you say, well, here is the null, and where is the maximum likelihood? I mean, what is the top of the mountain? They're very far from each other. That's what you do with the score test. With the likelihood ratio test, what you will do is you will measure this high and you will measure this high, and you will see the difference. And you say, oh, they are very far, because there you say, I cannot see it. When you do the score test, I cannot see it. With the likelihood ratio, you will just calculate how high is this point, how high is this point. And then you calculate the difference between the two. And with the wall test, you just see the difference on the horizontal axis. This is the three way these tests work. Okay, now we are going to study a little bit of more technical things. We are going to go deeper a little bit into the difference between these three tests, the holy trinity of a statistical inference. Sorry for that. Because as I said, they are under the null asymptotical equivalent. These are tests that are widely used, but they can be different in some substantial ways. And that's what I'm going to try to show you today here. And one of the most important ways in which they can differ is when you take into account the concept of invariance. What is invariance? Well, typically, you would like your scientific theory to be invariant to certain transformations of the data, or to be invariant to certain transformations of the parameters you are considering. So a widely acceptable principle is that inference should not depend, at least not crucially, on arbitrary elements. For instance, if I measure weight in kilograms, or I measure weights in grams, and I'm testing the hypothesis that the average bird's weight in Limburg is 3.3, I would like my test to give me the same results, whether I use grams or kilograms, right? Because what is the point? It's just a different scale, but essentially it's the same. That's invariance. So you would like your statistical test to be invariant to, for instance, the measurement scale you're using. Is the likelihood ratio invariance? If I use kilograms and grams, can I going to get the same? Is the wall test invariant? If I use kilogram and gram, can I going to get the same? Is the score test invariant? So this is an important question. And the answer will be rather interesting. It's a little bit technical. We will need to go a little bit technical here, but I think you could understand that this is an important issue. So for instance, when the parameter space is transformed in a one-to-one manner. So if I don't work with theta, but I work with theta squared. Or if I don't work with theta, but I work with 2 times theta, I don't know, to the power 3. Well, if I transform my parameter space in a one-to-one fashion, I would expect my procedures to give me the same results, whether I work with theta or I work with theta to the power 3. I would expect, if I test in the hypothesis theta equal to 0, I would expect that I would get the same kind of result, because one hypothesis is 0 if and only if the other one is 0. So this is the type of things we are going to analyze now. Are my tests invariant? What are the invariance properties of this holy trinity? And for instance, a very important issue in invariance is the measurement units. So if I use grams or kilograms, I'm going to get the same results when I test my hypothesis. If I use meter or kilometers, I'm going to get the same result. This is the type of things we are going to evaluate. And we're going to consider two different types of invariance. Invariance to equivalent representations of the null hypothesis. So you can write the null hypothesis in one way, or you can write it in another way, which are completely equivalent. For instance, the null can be theta equal to 1, right? That's my null hypothesis. Theta is equal to 1. Well, I can write that in another way. I can write that like the logarithm of theta is equal to 0. And these two hypotheses are equivalent, because theta is equal to 1 if and only if the logarithm is equal to 0. And in that case, you would expect that you're going to get the kind of the same results, because the two hypotheses are equivalent. And this is one type of invariance we're going to consider. If I write the null hypothesis in two ways which are completely equivalent, are these tests going to give me the same results? Or the answer to the question will depend on how the question is formulated. That would mean that I will write the null hypothesis in two equivalent ways. So I'm formulating the question in two different ways that are equivalent, and I'm getting different answers. Is that possible? And the second type of invariance we're going to analyze is the invariance to transformation of the variables that leave the form of the model and the null hypothesis equal. So we transforms a lot of time the variables. Just we use box and cost transformation to make our data more normal. We use a transformation of the data, but let's assume that we transform the data in such a way that the form of the model, the fundamental form of the model, and the null hypothesis we want to test stay invariants. They stay more or less the same. Are my tests going to give me different results if I transform the data in that way? That's another important type of invariant. So we need to formalize this a little bit. So we're going to use a little bit of math now, but it's unavoidable. So suppose that you have a testing problem and your null hypothesis is certain function of the parameters is equal to 0. That's the way you're formulating your null hypothesis. Psi of theta is equal to 0, where psi is just a function of the parameters. And you have seen that in the first lecture. You can go back there and watch it again, but a transformation has something associated with it that is called the Jacobian. And what is the Jacobian? Is the derivative of this function with respect to theta. That's it. That's the Jacobian. And we are going to consider that theta is a vector. It has p components, right? For example, if you go back to slide 28, if you go back to slide 28, let me go back there a second. If you go to slide 28, let me go there. Well, it's not that slide exactly, apparently something here. But essentially what that slide, the null hypothesis there was, let me write it down, the null hypothesis was theta equal to theta 0, right? This is the one we were considering when we were developing the three tests, the Holy Trinity. And that hypothesis is just consider the psi function that is theta minus theta 0 equal, theta minus theta 0 equal to 0. This hypothesis will be equivalent to this hypothesis. So this is a very naive general way to write a null hypothesis. Certain function of the parameters is equal to 0. Fine. Now, if you want to test that hypothesis, you can use the Holy Trinity. You can use the likelihood ratio test, you can use the likelihood ratio test, the Wald test, and the score test. You can use the three of them. And here you have the formula for these tests. So you have the three tests, you can use whatever you want. The only thing you need, of course, you need to estimate the theta here, the theta under the null, the theta under the alternative. You need to estimate the efficient information metrics. In the previous lecture, we saw 3 different ways of estimating the efficient information metrics. You can go back to the lecture and refresh this. But you can construct a test for that. So you have this null hypothesis over here, and you can analyze this null hypothesis using the Holy Trinity: likelihood ratio, Walls, and a score test. Now, let's do the following. Suppose that you have a family of transformations, a family of function psi. These functions should have some properties. They should be continuously differentiable functions. What that means that they are smooth, that you don't have weird behavior like peaks and things like that. So suppose that this function you're using to construct the null, psi of theta equal to 0, is kind of a nice hilly function, doesn't have peaks, it's kind of smooth. And suppose that in this family you have several functions psi that satisfy that property. And suppose that if you have 2 functions in that family, psi on psi1, they all belong to the family. Suppose that psi is equal to 0 if and only if psi1 is equal to 0. So these things are true simultaneously. So what you're saying essentially is that all functions in that family will give you exactly the same null hypothesis. Right? Because if you formulate the null like psi equal to 0, psi of theta equal to 0, or you formulate the null like psi 1 of theta equal to 0, one is true if and only if the other one is true. So they're equivalent hypotheses. So you will say that the test is invariant with respect to the formulations in psi, with respect to the formulations of the null hypothesis using different functions inside, when the result of testing this hypothesis is the same for whatever function in psi. So whether I write psi of theta equal to 0 or I write psi 1 of theta equal to 0, the test is going to reject both or not simultaneously. I will get the same answer to this question, which makes sense because these 2 null hypotheses are actually equivalent. One is true if and only if the other one is true. The only thing I'm doing is I'm reformulating the question with different words, but the question is the same. So you're going to say that if a test is invariant to that, so whether I write it in one way or the other one, I will get the same, I will reject or not simultaneously. You say that the test is invariant with respect to equivalent representations of the null hypothesis. Now, from the three tests we have studied, which ones are invariant? Well, the likelihood ratio test is invariant. It will give you the same answer irrespectively of how you formulate your question. The score test is also invariance. It will give you the same answer irrespectively of how you formulate the question and irrespectively of how you estimate the feature information matrix. But the Wald test is not invariant. And that means that basically it can give different answers to the same question, depending on how the question is phrased. That's the problem with the Wald test. And I will give an example. Suppose that you're testing the null hypothesis theta equal to 0, right? And suppose that the maximum likelihood estimator is 1. And that the variance of the maximum likelihood estimator is 0.01, right? What would be the Wald test? Well, the Wald test in this case would be the maximum likelihood estimator minus 0, what you have here, you divide by the variance, which is 0.01, and this is going to be 100, and under the null, this follows a chi-square distribution with 1 degrees of freedom, and then the p-value you get is given here. So it's a rather significant p-value. So when you use the Wald test to test this hypothesis, you reject it. Now, suppose that you will write the null hypothesis in a different way. So you now consider a new value, a new parameter epsilon, that is theta to the power a. And a is any odd positive number. Of course, the maximum likelihood of theta, the only thing you need to do is to plug in here now the maximum likelihood of epsilon. The only thing you need to do is to plug in here the maximum likelihood of theta, which is 1, it's given over here. So the maximum likelihood estimator of epsilon is 1. Now, suppose that you want to test the hypothesis. So here you have theta equal to 0. Suppose that you want to test the hypothesis epsilon equal to 0. Now, theta, the null hypothesis theta equal to 0 and the null hypothesis epsilon equal to 0, these two things are true or false at the same time. You are just rewriting the question with different words. But this one is 0 if and only if this one is 0. Now, let's apply the Wald test now to test this. Well, you will have the maximum likelihood estimator of epsilon, which is given here. This is going to be equal to 1 divided by the variance. And the variance is going to be now 0.01 times a squared, because this is theta, you have this a over here. And what you get here is this value, 100 divided by a squared. And as you can see, if a is equal to 25, just specify a value there, then you're going to get a value for the Wald test, which is 0.16, and you will get a p-value of 0.69. So you are getting a different answer to your question. If you test this hypothesis, you will reject it. If you test this one with the same data, you're using here the same data, then you will not reject it. But these two things are equivalent. So the likelihood, the Wald test has that problem. The answer to the questions depend on how you ask the question. And that is a problem of the likelihood, the Wald test. The likelihood test will give you the same answer. The score test will give you the same answer. The Wald test will not give you the same answer. It depends how you write the null. If you have two null hypotheses completely equivalent, you may get different results. Now, I will give a very fast idea of the second invariance. The second invariance is, well, you have your data. Your data is a response, and then you have a vector of covariates, and you postulate a model for that data. You postulate that the distribution of the outcome given the covariates is a probabilistic model that depends on certain parameters. That's your model. And now you transform your data. So you construct a new data set that is given here by the asterisk. You have a new response, you transform the response, you transform the covariate. So you transform the response in this way as a function of the original data, and you transform the covariate this way. Why you want to do that? Well, many times you transform the data just to achieve normality, to achieve homoscedasticity, etc. So now you have a new data set. Before you have this data set, which is the response and the covariates. Now you have a new data set asterisk, which is here. And it's just a transformation of the original data. Now, let's assume that you postulate a model now for the due data. You postulated the model here. And let's assume that you transformated the data in such a way that this model has actually the same shape as the original model over here. The only difference is that the parameters, of course, will change. You will not use the same parameters as with the original data because you have transformed the data. But still, the transformation respects the model. The model doesn't change. If you have a normal distribution, the transformed data still has this kind of normal distribution of the model essentially stays the same, but you need to change the parameters. And so you now have a new vector of parameters and a new vector of data, but the model stays the same. And let's assume that you now want to postulate a null hypothesis in terms of the original parameters, the one that you had with the original data, or you postulate the hypothesis in an equivalent way, but now using the transformed data with the new parameters. Essentially, you are postulating the same type of thing. You have a null hypothesis with the original data, you transform the data, of course the null gets transformed because the parameters change, and you have these two hypothesis problem. I can test the original hypothesis with the original data set, or I can test the alternative hypothesis with the new data, the transformed data set after. But this transformation has respected the model and has has led to an equivalent null hypothesis. The question is, if I do this test with the original data, or I analyze this null hypothesis, I test this with the transformed data, am I going to get the same results, yes or not? Now, the likelihood test, again, will give you the same results. Well, you can transform your data if you respect the model, and then in the new transformed data, the new null hypothesis, you are going to reject that if and only if you rejected the null with the original data. The score test is invariant, but now you have to be careful because it's not always invariant. It is invariant if you estimate the information, the feature information matters in certain way. You have to be careful. And again, the Wald test is not invariant. So the Wald test has this invariance problem that if you reformulate the null hypothesis in an equivalent way, you may get different results. If you transform your data, even in a way that respects the models and leads to an equivalent null, you may get different results. So the Wald test has these invariance problems. And there is a very interesting paper, was Van Spitzer, was published in 1984, and he did the following. He used a regression model, and he used a Bose and cost transformation of the Y variable. And he showed that the values of the t statistics for the regression coefficients, which is essentially the Wald test, this test statistic is what you get with the coefficient tables in R. That values of the t statistics depend on the measurement units of the dependent variables. If you use gram or kilograms, you may get different results. If you're working with a model that use a transformed Y variable, Bose and cost transformed Y variable. So yes, the Wald test gets this problem with invariance. It's not an invariant test. Your answer to the question may depend on how you phrase it, may depend if you transform the data or not, and this is something you need to take into account when you're going to use the Wald test. And so I'm going to, you have the next, what comes here is an example. I'm going to leave this example as a homework. You can just go through it. It's just an example to illustrate this invariance property. So if you try to construct a confidence interval, you can also use a likelihood approach, you can use the Wald approach, and you can use the score approach. And you will see that the properties of that confidence interval are different. So for instance, when you calculate a confidence interval based on the Wald test, for a probability, you may get negative values. It's kind of weird. It's all related to these invariance properties of the test. So yes, they are asymptotically equivalent under the null, but they may satisfy different properties, right? And we have seen that if we are thinking in terms of invariance, then the best option will be the likelihood ratio test, the second best option will be the score test, and the worst option will be the Wald test. If you're just thinking about, well, if I formulate the null into equivalent weights, I'm going to get the same results, well, then you will get the same results if you use the likelihood and if you use the score, but not if you use the Wald. So even though they are asymptotically equivalent, you need to be careful here. You need to take into account other characteristics as well. And now we are going to see, that's the last part of the lecture, what happens if my model is wrong. because all these nice properties we have studied about the maximum likelihood estimators, as I told you, they're asymptotically unbeatable, consistent, efficient, asymptotically normal, unbiased, asymptotically unbiased. And all these, we can construct all these tests, the score test, the WALT test, the likelihood ratio test. And we can test all these nice hypotheses, simple hypotheses, composite hypotheses, etc. However, what all this works under the assumption that you got your model right. Remember what we are doing here. Don't forget that. So you have your data set. You did your experiment and you collected the data. And you have the observations Y1, Y2, Y3, and so forth. And you have probably covariance as well there. Now you are going to make a very important assumption. You're going to make the following assumption. The data generating mechanism, that latent procedure that is producing these outcomes, can be modeled with a probabilistic model. That's an assumption. That's an assumption. And you're going to specify, because we are doing parametric statistics, you are going to specify the model. So we are going to say, well, this data is being generated by certain probabilistic model that depends on Y, depends on certain covariates, and has a set of parameters. So you are specifying the shape of this data generating mechanism, and then the only thing you need to do is to use the data to estimate theta, to make statements about theta. But all this is based on the idea that you got this right. And what if you don't? What if you mis-specify your model? What are the consequences that that will have for my conclusions? Well, what we do typically is we were working now in the likelihood paradigm, and what we do is, well, once you specify your model, you can write your log likelihood in this way, which is, if you got the model right, the likelihood is the probability of the data, but you look at it as a function of theta. So here you have the log likelihood. And what you do is you maximize that log likelihood, and then you get the maximum likelihood estimators. And if you got the model right, if this thing over here is right, then your maximum likelihood estimators are unbeatable. They are consistent, asymptotically normal, they reach the Cramer-Rao lower bound, etc. But this is assuming the model is right. Why if you got your model wrong? Well, by the way, you calculate the maximum likelihood by solving the scores equation. So what you do is you solve these equations here equal to 0. You apply Newton-Raphson or something like that to calculate the roots of the score equation. Now, when you're going to say that the model is right, when I'm telling you all this works if the model is right, what do you mean? Well, what I mean is that there is a value of theta, let's call it theta 0, that if you plug it here in your model, that's it. That's really the way the data is being generated, right? If that properties is there, you say that your model is correctly specified. So there is a value of the parameters theta 0 that if you specify it, if you plug it in your model, then this is really the data generating mechanism. If that is true, you have gotten your model right. And in that case, the maximum likelihood are consistent. So you can get as close as you want to the true theta. You just need to have enough information. That's the consistency property of the maximum likelihood. So that's what we mean. But what if I got the model wrong? By the way, then you have that maximum likelihood also are asymptotically normal. That means that if you construct this new random variable here, if you construct this new random variable here, so you construct root square of n times the maximum likelihood minus the true value, this is going to converge in distribution to a normal distribution, where you have all these nice properties. Maximum likelihood asymptotically normal, with mean theta 0, the true value that produces the real data generating mechanism, and with a variance covariance matrix that reaches the lower bound of the Cramer-Rao inequalities, the inverse of the Fisher information. Now, suppose that you got your model wrong. So your model, the real generating mechanism is not like this, but it is like this. So yes, you have the same outcome, but the data generated using different covariates and different parameters. So you completely got this wrong. That can happen in practice. You may specify your model. So your model, the real data generating mechanism, doesn't depend on X and doesn't depend on theta. Actually depends on Z and gamma. It's a completely different story, and you got it wrong. What happened now if I use maximum likelihood? using the wrong model. If I keep working with the wrong model, what are the consequences? Well, this is very interesting because there is something called the Colbert Labor Information Criterion, the CLIC. And this Colbert labor information criterion is given here. Is the expected value now with respect to the true model, with the true the probabilistic distribution of the logarithm of the true data generating mechanism divided by your model, but the misspecified data generating mechanism. And if you want, this is can be interpreted as a distance. You can interpret this value as a distance between the true data generating mechanism and your model. You got your model run, and this quantity here quantifies the distance, roughly speaking, the distance between your model and the true model, right? Now, if you apply maximum likelihood now using the wrong model, what you can prove is that the maximum likelihood estimator will converge to the value of theta that minimizes this quantity. So the maximum likelihood estimator will converge to the value of theta. We're going to call that theta asterisk. That maximizes, not maximizes, but minimizes. That minimizes the distance between your model and the true. So maximum likelihood is really quite a very interesting procedure. Because even if you get your model wrong, and you apply maximum likelihood, what you're going to do, the value you're going to get to for your parameters theta, the thetas are wrong. This is not the way the data are being generated, but maximum likelihood will give you the value of theta that makes your model closest to the true model. And that's in itself kind of a valuable result. So even when the model is wrong, your inference may be wrong because you are using a completely wrong model. But maximum likelihood try to give you the value that makes your model as right as possible in the sense of as close to the true as possible. Now, what are the properties of the maximum likelihood estimator if your model is wrong? Well, to do that, we need, again, a little bit of a math here. So let's consider these variance, covariance matrices here. These are actually what we saw before. This is like the Bayesian of your model. Remember that your model is wrong. And then this is now the matrix of this cross product. That if the model is right, these two representations, you calculate the expected value of AN is A, the expected value of Bn is B. If the model is correctly specified, you can show that these two things are going to be equal. That's the information equality that we saw in the previous lecture. But if the model is wrong, these two things are not going to be equal. And what you can show is that the maximum likelihood estimator, when you calculate it with the wrong model, is going to converge asymptotically again to a normal distribution. But now a normal distribution that will be centered on these new parameters is the parameter that makes the model closest to the true data generating mechanism. And now the variance covariance metric has this specific form here, and this is what we call the sandwich estimator. Now remember this because we are going to use this later on in logistic regression, in Poisson regression. And it's just to take into account that sometimes your model may be misspecified. If you got your model right, then the maximum likelihood is going to converge to the true value of the parameters, and this matrix over here, this sandwich matrix, estimator matrix over here, is going to converge just to the inverse of the Fisher information matrix. You're going to get the classical result. But if your model is not correctly specified, then you're going to converge to this value of the parameters that minimizes the distance between the model and the true, and you will have these asymptotic normal results. So, what about hypothesis testing? Well, suppose that you are testing this hypothesis over here, right? With the model is misspecified. The model is wrong. So the marginal likelihood may not be converging to theta 0, may be converging to theta asterisk. And you're interested in testing this hypothesis like we saw before, a function of theta asterisk equal to 0. Here you have the Jacobian, etc. Sometimes your model may be misspecified, but the theta asterisk may still be equal to theta 0. We are going to see that later on. We are going to see that later on. We are going to see situations, for instance, with Poisson regression, in which your model may be wrong, but still the beta coefficients in the regression, you may get them right. Now, how can I do test? You cannot apply the classical test because your model is wrong, and the score test, the wall test, and the likelihood ratio test, they assume the model is right. Well, here is the thing. You can construct a appropriate wall test and a score test if the model is misspecified. Here are the versions for the wall test. As you can see, it's very similar to the wall test when the model is right, but you use now a different matrix here. You don't use the inverse of the Fisher information, you use a sandwich estimator matrix over here. That's what you do. You use the sandwich estimator. And you can do the same for the score test. You can construct a version of the score test that works even when the model is misspecified. But again, you need to use the sandwich estimator over here, right? This is what you need to do. And if you do this, you can test this hypothesis over here in a correct way. And if you got lucky and your misspecification satisfies this over here, then you will have a valid test for the parameters in your model. But you need to use a difference covariance metric. You need to use the sandwich estimator. What about the likelihood ratio test? Very important. Under misspecification, the wall test and the score test will still be equivalent under the null. So they will converge in probability to zero. They will have the same distribution, a chi-square distribution with degrees of freedoms that are the number of parameters in the full model minus the number of parameters in the null model. So as I said previously, you are going to get the same results under the null with the wall and the score test, even when they are misspecified. So what about the likelihood ratio test? Well, the likelihood ratio test is going to get into trouble when you have a misspecification. Actually, if the model is misspecified, then under the null, the likelihood ratio test is not anymore asymptotically chi-square. So there are versions for the score test, there are versions for the wall test that will be able to work under misspecification. For the likelihood ratio, the situation is more difficult. However, as we have seen before, the likelihood ratio test has better invariance properties than the wall test. So I think we still have a little bit of time, so maybe we can go to the case study we were seeing before. I tried to give first the new material, but we have still time, it's until 5. So let's see the example we were discussing. Suppose that you have a simple single parameter theta, and you are interested in testing the hypothesis theta equal to theta 0, so which is a simple hypothesis. Now, if you have, I told you that you can construct a test for a hypothesis based on a confidence interval, but you can look at it in the other way. So you can start from the test, and then you can construct a confidence interval. And the way to do that is, well, suppose that you have an alpha level two-sided test. You can construct based on that test a confidence interval around theta just by seeing the values of theta, the theta zero that does not reject the null hypothesis. So you calculate all possible values of theta 0 for which the null hypothesis will not be rejected, and that will give you, if the test is a 5% test, it will give you a 1 minus alpha, in this case a 95% confidence interval. So suppose that you have a critical region to define your test, which is the certain statistics evaluated in theta 0, which is what the null specifies, is greater than certain value C, then you reject. That's your test. So you calculate then the confidence interval, 1 minus alpha percent confidence interval, by calculating the values of theta 0 that guarantee that the test is not rejected, that this is smaller than C alpha. So if you solve that equation, you calculate the values of theta 0 for which this is smaller than C alpha, like we have here, then these values, this solution, are going to confirm a 100% confident, 100 times 1 minus alpha percent confidence interval. So let's do that in practice. So suppose that you're testing a hypothesis, a null hypothesis about a proportion. So your null hypothesis is pi is equal to pi 0. You can test that using the wall test. And here you have the formula for the wall test. And now what you're going to do is you're going to consider the values of pi 0 for which the wall test will not reject this hypothesis. And that will give you the confidence interval. If you do that, you get actually a classical confidence interval for proportions. Here you have. Now you can test that hypothesis using, for instance, the log likelihood test. So here you have the the likelihood ratio test. So here you have the log likelihood, and here you have the likelihood ratio test. And what you have to do now is you need to calculate the values of pi0 that will lead to a value smaller than certain C alpha, in this case 0.05 for alpha. And like that, you can calculate a likelihood ratio confidence interval. And if you do that, then you get the likelihood ratio confidence interval. Now, suppose that I'm having a little problem here with my mouse. Suppose that you want to use now the score test to test this hypothesis over here. Now, what is the score test? You need to calculate the score function, which is given here. And then the score test, here you have the formula for the score test. And then you're going to determine the values of pi0 for which this score test will not reject the null. And then you get a confidence interval. So inverting the score test, it gives you a confidence interval that is sometimes called the Wilkinson interval. You can see the reference in Agresti 2007. So let's do that with a case study. Suppose that you have a sample of 10 independent observations and you got just one success. So this is a binomial distribution. In 10 trials, you got one success. Now, you want to calculate a confidence interval for pi, which is the probability of having success. In this 10 trial, the probability is that each independent trial, you have a y1, a y2, etc., until a y10, and the probability that any of these outcomes will be equal to 1, the probability is pi. Now, a while 95% confidence interval is given here, and you immediately see there is a problem. We are getting negative values for a probability. So the first deficiency of the while interval is that it may include values that are invalid for the parameter. Now you can solve that problem. You can calculate, for instance, the while confidence interval not for the parameter, but for a transformation of the parameter, and then you back transform to get your confidence interval for the parameters. For instance, you can calculate the while test not for pi, the while confidence interval not for pi, but for the odds of pi. And then once you have the confidence interval for theta, you back transform to get a confidence interval for pi. And if you do that, you solve the problem, because now you get here the wild confidence interval for theta, and when you back transform it, then you get a confidence interval for pi that doesn't have any negative value. It's between 0 and 1, which is a probability. So as desired, this interval only includes valid values for probability. Now here is the problem. The problem is that if you use two different transformations, if you use theta, which is the log odds, or if you use another transformation theta 1, and you calculate a confidence interval, you back transform, you get different results. That's the problem with the invariance of the wild test that we saw before. That if you test equivalent hypothesis, you may get different answers, but this is a manifestation of that. So if you calculate it for the log odds and you calculate it for another transformation of the probability, you have these two confidence intervals, you back transform, then you get different confidence interval for pi, which is kind of inconvenient. Now, the confidence interval for the likelihood ratio test, based on the likelihood ratio test. So how is this? Well, if you have now the likelihood ratio test, when you will not reject? Well, you will not reject when the likelihood ratio test is smaller than 3.85 approximately. So what you need to do is you need to find the values of pi that satisfy this inequality. This is an equation you have to solve. So it's essentially these values over here. This will be your confidence interval. And if you look at it, then you see already some nice characteristic of the likelihood ratio test. For instance, all the values are valid probabilities, and they will always be. You see that the upper limit here is rather smaller than the one you got with the wild test. So it gives a kind of a more precise results. Now, if you transform the parameters and you calculate the likelihood ratio confidence interval based on theta and you back transform, then you're going to get exactly the same interval. It's not like the wild test. You're going to get, if you calculate the confidence interval now for the transformation of pi and you back transform, doesn't matter which transformation you do, you're going to get always this confidence interval for pi, which is transformation invariant. This is related to what we saw before. So if you calculate the confidence interval for the log odds using likelihood ratio and you transform, you're going to get the same answer to your question. Nothing is going to change. And well, this is basically, for instance, some of the properties of these three procedures. So let me check the questions. We still have some time. Let me check the questions that you were asking today. So the first question was why the confidence interval based approach is less used. That's a good question. They said the p-values approach has been criticized a lot. That's true. I don't have an answer for that. And people love p-values, maybe because p-values give this black and white answer, this yes or not answer. So, but indeed, this uh, actually confidence intervals will be a much better approach. But for some reason that somehow escapes my understanding, people doesn't use so much confidence intervals when they are testing hypotheses. Could you please update the slides on Toledo? Really, I think they are the same. I'm going to check that. Somebody asked me, is this, we were talking about misspecification, is this quasi-maximum likelihood? We are going to discuss that later on when we start just seeing the specific models like the logistic regression, and we are seeing, Poisson regression. There you have indeed what we call quasi-maximum likelihood. So it's a good question, but we're going to answer it later on. Should we learn it by ourselves or should we skip it? You should not skip anything. You should try to, there are sometimes may happens that there are some examples. It will be typical examples that I will tell you, well, studying out the samples independently. But please have a look at everything, try to understand everything. Yeah, somebody asked there. So try indeed to read everything, to try to get an understanding of it. Is the oral exam per student or per group? The oral exam is individual. So you work on the project in tutorial groups, but the oral exam is an individual exam. So I will have a little chat with each of you individually. Which back transformation would be valid for the wild test, considering the non-variance? Well, there is not like such a thing like a valid transformation. I mean, in this case, we use the log of odds to just get a correct range of the data. And that's indeed one of the problems of the wild test, that is not invariant. So you may get different results if you use different transformations, and that's indeed inconvenient. However, as I said before, there is not a black and white answer here. As I told you, if you're thinking in terms of invariance, then well, if you're using invariance as the criterion, then of course the wild test is the worst option because it's not invariant. It's not invariant, and the likelihood test is, and the score mostly is invariant. But if you are thinking about misspecified models, then the likelihood ratio is the more problematic because there are versions of the wild test and the score test. To work on the misspecification, the likelihood ratio is more problematic. If you have missing data, you have the same type of situations. There are procedures that allow to handle missing data in the wild test and in the score test rather straightforwardly. But for the likelihood ratio test, if you have missing data, is more problematic. So that's why it's good to have all these variety of tools, because reality is very rich and you may need in some situations certain properties and in another situation other properties. So let me give you a very little summary about what we have seen, because this is just the last part. So here is what you do. You have collected data in an experiment. You have observations, and you assume that this observation has been generated by some kind of latent mechanism. There is a common mechanism that produces these outcomes. And this mechanism is modeled with a probabilistic model that depends on a vector of parameters theta. That's an assumption, right? So you assume that birth weight is generated by some kind of latent mechanism that can be modeled with certain probabilistic model that depends on parameters theta. That's an assumption. Now, if you got that right, and what do you mean by you got that right? So suppose that there is a value of the parameters, we will call it theta zero, that if you plug it in your model, then that's it. That's the real way the data is being generated. If that is true, if there is a value of the parameters that made the model the really true generating mechanism, then you say the model is specified. Now, if that is right, then you can make all this inferential machine start working, right? And this inferential machine is, well, we have a way to estimate these parameters, which is called the maximum likelihood methods. And this is a pretty good way of going to estimate the parameters. Why? Because, well, actually, it's a very intuitive idea. You're going just to find the estimator that maximizes the probability of observing the data, which is quite logical because you did observe the data. So this data should not be that weird. And this maximum likelihood estimator is going to have a lot of nice properties asymptotically. So in asymptotopia is the king. What I mean by that is going to be unbiased asymptotically, is going to be efficient asymptotically, is going to be consistent, is going to be normally distributed, is just a very good estimator asymptotically. And also, based on this likelihood machine, you can generate tests because you typically write your scientific questions in terms of statements about the parameters in the model. And you can test this hypothesis using this likelihood-based test. And we have seen what we call the holy trinity of inferential statistics, the score test, the likelihood ratio test, and the WAL test. Now, if you got your model right, then all this machinery works. And you can show that all these three tests, if the null is true, they will give you the same results. So it's not that if the null is true, one of them is going to give a result, the other one is going to. If the null is true, they will all give you the same result. We call that they are asymptotically equivalent. So you can use them. Whatever model you specify, doesn't matter. The model is P of y slash x colon theta. Whatever, you give me a model that satisfies this property, a model that satisfies some general condition, and all this machinery can be used. It's a very general approach, this likelihood machinery. Now, these three tests, they are equivalent to the null, but that doesn't mean that they are always the same. We saw, for instance, they differed in some important ways. For instance, if you're dealing with invariance, if you are dealing with, well, if I represent the null in two different ways, but these ways are equivalent, well, these tests may give you different results. The likelihood is going to be invariant, the score is going to be invariant, but the WAL test will not be invariant. If you transform your data and you but you transform it in such a way that the model, the shape of the model stays the same and the null hypothesis is equivalent to the one you have with the original data. Again, the likelihood ratio is always invariant. The score test is invariance if you use the right estimators for the feature information metrics. And the WAL test is again non-invariance. Actually, the WAL test may be sensitive to the units you're using to measure the measurement units. So even though they are equivalent under the null hypothesis asymptotically, they are not exactly the same. They have different properties. And finally, we saw that if you misspecify your model, because there is a chance that you got it wrong, there is a chance that you got it wrong. Reality is extraordinarily complex, so you may be working with the wrong model. Well, if that is the case, and you applied the whole inference, all this likelihood machinery, but using the wrong model, then what? Well, to a certain degree, maximum likelihood does the best he can do. He will give you an estimate for the parameters in your wrong model, so an estimate for these wrong parameters that make your model closest to the true model. And this is the best he can do, right? It cannot give you the right answer because you're using the right tool, the wrong tool, but it will give you the estimate for the parameters that pushes your model as close as possible to the true model. So try to minimize the errors somehow. So good is the maximum likelihood procedure. And then we have seen that if you're trying to test hypotheses on your wrong parameters, in some situations, we are going, that's what we call the quasi-likelihood, and we're going to see all that in certain details. So in some situations, your model is misspecified, but still the parameters are right, let's say it that way. And you still want to make tests about these parameters. Some part of your model are wrong, but let's say you still specify the mean in a correct way. The distribution is wrong, but the mean is correctly specified. In many situations, then your parameters are going to be fine. The maximum likelihood are going to converge to the true value of the parameters. And if you want to test something about these parameters, then there are versions of the WAL test and the score test that will give you still correct answers under misspecification. But you need to use this sandwich estimator. The likelihood ratio is more problematic. The same if you have missing data. They are extensions of the WAL test and SCORE test for the case in which you have missing data. The likelihood ratio becomes more difficult. So as you can see, the likelihood ratio has a lot of nice properties, invariance, etc. But in some situations, the worst test with respect to invariance, which is the WAL, may be preferable. So it's a difficult word, guys. So you need to just analyze in which situation you are, what properties of a test or a confidence interval are most important in this specific situation you are, and then make a wise decision. So this is it. This has been the lecture for today. And today we finish all this theoretical inference part. And from the next lecture on, we start studying the GLM. We are going to start by the linear regression, the best known case, and then we are start building up to the more, let's say, complex models if you want. We're just going to see logistic regression, many issues related to logistic regression, Poisson regression, all issues related to Poisson regression, gamma regression, and then the general formulation of GLM. I'm going to check what you ask about the exam. I'm going to check also something that they have said here about slide 19. I'm going to check that as well. So thank you for being here today, and we will definitely see each other next week. Have a nice weekend, because I will not see you anymore until Monday. Bye.